Right now, all around you, there is a faint glow of light that has been traveling through space for almost 14 billion years. It's the oldest light in the universe, a cosmic echo from a time before stars, before galaxies, even before atoms as we know them. This isn't science fiction, it's real, and it holds the deepest secrets of how everything began. We call this light the cosmic microwave background, and it is one of the most profound discoveries in the history of science. It's the afterglow of the Big Bang itself, a snapshot of the infant cosmos imprinted across the entire sky. But what if I told you this ancient light isn't just a relic? It's a riddle filled with whispers from the dawn of time that we're only just beginning to decode. Hidden within this glow are clues that challenge everything we think we know about the universe's birth and evolution. Tiny fluctuations in its temperature, patterns in its polarization, anomalies that simply don't fit our models. These aren't just random noise. They're cosmic messages waiting to be understood. Some of these mysteries hint at physics beyond our current understanding. Others raise questions about the very nature of time, space, and reality. Why does the universe appear so uniform in some ways, yet so strangely lopsided in others? What caused the ripples we see in this primordial light? And are we missing something fundamental about the forces that shaped existence as we know it? This is a journey into the unknown, a voyage back to the very beginning. In this video, we'll explore 30 of the most compelling mysteries of the cosmic microwave background. These aren't just scientific curiosities, they're gateways to a deeper truth about our place in the cosmos. Each one invites us to look closer, think bigger, and wonder more. So settle in and open your mind, because we're about to dive into the oldest story ever told, written in light, waiting for us to read it. Our first great mystery asks a simple but profound question. How did the universe get its temperature so perfectly even? When we look at the cosmic microwave background, we see it's almost exactly the same everywhere. From one side of the sky to the other, the temperature varies by less than 1 part in 10,000. To put that into perspective, that's smoother than a billiard ball blown up to the size of the Earth. This incredible uniformity is what scientists call isotropy, and it presents a monumental puzzle known as the horizon problem. Think of it this way: the light from these two opposite sides of the sky has taken nearly 14 billion years to reach us. But here's the catch: the universe itself wasn't old enough at the time this light was emitted for these two regions to have ever swapped a single photon, not even one. They were causally disconnected, separated by a distance greater than light could have possibly traveled in the age of the universe at that moment. It's like two people standing in separate, soundproof rooms miles apart, starting to hum the same exact note at the same exact time without any way to communicate. How could they possibly coordinate that? According to the standard laws of physics, there is no mechanism for these vastly separated areas to have come into thermal equilibrium. They should have noticeable differences, distinct temperatures, unique histories, and yet they don't. This is where one of the most brilliant and controversial ideas in modern cosmology comes in: the theory of cosmic inflation. The proposed solution suggests that in the very first fraction of a second after the Big Bang, the universe underwent a period of exponentially rapid expansion. It wasn't just expanding quickly, it was expanding faster than the speed of light itself, stretching a region smaller than a subatomic particle to something larger than our entire observable universe in less than a billionth of a billionth of a billionth of a second. This incredible growth spurt would have taken a tiny, homogeneous patch of the primordial cosmos and stretched it across the entirety of existence, ironing out any wrinkles or temperature differences and setting the stage for the perfectly smooth background we observe today. While inflation is an elegant and powerful solution embraced by many cosmologists, the debate is far from settled. The how and why of inflation remain deeply mysterious. What force could have powered such an extraordinary event? Was it a field of energy, a particle we haven't discovered, or something entirely beyond our current physics? Some scientists are exploring alternatives, questioning if inflation is the only answer or if we need to reconsider our fundamental understanding of gravity and spacetime. The horizon problem forces us to confront the very first moments of creation, a realm where our known physics breaks down and the true nature of the universe reveals its deepest secrets. But if the horizon problem makes the universe seem almost too perfect, our next mystery presents the exact opposite challenge, a strange, specific imperfection that refuses to be explained away. As we meticulously chart the subtle temperature variations of the cosmic microwave background, one anomaly stands out like a cosmic sore thumb, a vast, startlingly cold region known simply as the cold spot. This isn't a tiny dip in temperature, it's a colossal patch of sky enormous enough to contain thousands of galaxies, where the ancient light is significantly cooler than the models predict it should be. For years, astronomers have debated whether this is merely a statistical fluke, a trick of the data, or something far more profound, a crack in the foundation of our cosmological understanding, and perhaps even a window into a reality beyond our own. The most straightforward explanation, and the one scientists initially gravitated towards, is that the cold spot isn't a feature of the primordial universe at all, but rather a later illusion created by a foreground object. The idea was that a vast, largely empty region of space, a cosmic supervoid, might lie between us and the CMB in that direction. As the CMB light travels through such a void, it would have to climb out of a gravitational well. This struggle against gravity saps the light's energy, causing it to redshift and appear cooler to our instruments. It's a well-understood phenomenon called the integrated Sachs-Wolf effect. The hunt was on to find this proposed supervoid, and indeed, surveys have found a large underdensity of galaxies in that general area of space. The problem: it's just not nearly big enough or empty enough to account for the dramatic coldness we observe. The numbers simply don't add up, leaving the supervoid theory as an intriguing but insufficient answer. With the conventional explanation falling short, cosmologists have been forced to consider far more exotic possibilities. One of the most mind-bending theories suggests that the cold spot could be evidence of a collision with another universe. This idea stems from the multiverse concept, often linked to eternal inflation, which proposes that our universe is just one bubble in a vast, frothing sea of countless other bubble universes. If another universe bubble had bumped into ours in the distant past, the energy released at the boundary of that colossal collision could have imprinted a specific, circular signature onto our cosmos, a signature that looks an awful lot like the cold spot we see today. It's a staggering notion that we might be seeing the bruise from a primordial encounter with an entirely separate reality with its own distinct laws of physics. Of course, the most conservative stance is to dismiss the cold spot as a statistical anomaly, a 1 in 100 fluke that, in a dataset of millions of pixels, was bound to appear by pure random chance. Yet, as our measurements become more and more precise, the cold spot's statistical significance persists. Its sheer size and profound coldness make it an outlier that is incredibly difficult to explain away with simple randomness. It stubbornly refuses to be smoothed over by better data or more powerful telescopes. This persistence is what fuels the ongoing fascination and debate. It represents a tantalizing clue that our standard model of cosmology, for all its success, might be incomplete, whether it's evidence of exotic physics, a multiversal collision, or something we haven't even dreamed of yet. The cold spot remains a compelling and unanswered challenge, a cold splash of mystery on the oldest map in the universe. So just as the cold spot challenges us with a single, giant imperfection, another mystery woven throughout the entire cosmic microwave background map threatens a principle even more fundamental to cosmology. This one is so unsettling that scientists half-jokingly named it the axis of evil. It sounds like a title from a science fiction thriller, but its implications are very real. The mystery is this: certain large-scale patterns in the CMB's temperature fluctuations appear to be oddly and inexplicably aligned with the plane of our own solar system. This is a profound problem because it directly challenges the cosmological principle, the bedrock assumption upon which all of modern cosmology is built. This principle states that the universe on a large enough scale is homogeneous and isotropic. It should look the same in every direction and have no special center or preferred axis. There should be no up or down in the cosmos, no universal north or south. The universe shouldn't care about the arbitrary orientation of our tiny little solar system. And yet, the data seems to suggest that it might. The alignment manifests in a few different ways. One of the most striking is in the behavior of the quadrupole and octupole moments, the terms scientists use to describe some of the largest scale patterns in the CMB's temperature variations. These patterns, which represent the biggest ripples in the fabric of the ancient universe, show a surprising amount of alignment with each other. Even more bizarrely, their so-called preferred axis also seems to line up with the ecliptic plane, the path the sun and planets trace across our sky. It's as if the universe's largest structures are somehow aware of our local celestial neighborhood, a suggestion that is, scientifically speaking, deeply disturbing. The immediate and most logical conclusion is that this is not a feature of the universe at all, but an artifact of our own observation. Perhaps it's a subtle systematic error in how we've processed the data from satellites like WMAP and Planck. Maybe it's an unforeseen contamination from within our own solar system, dust, the solar wind, or some other local phenomenon imprinting itself on the data and creating a phantom signal. Scientists have searched tirelessly for such an error, checking and rechecking the instrumentation and data analysis pipelines. While some minor foreground effects have been identified, none have been sufficient to completely erase this persistent and peculiar alignment. Its signal, though faint, stubbornly remains in the cleansed data. If it's not an error, then the implications are staggering. It could mean there is something fundamentally wrong with our understanding of the universe's geometry on the largest scales. It might be a hint of physics operating before the Big Bang, a fossilized imprint of an era that set a preferred direction for the cosmos. Some theorists have proposed it could be evidence that our universe is not infinite and isotropic, but has a more complex, perhaps even rotating topology. The very idea that we might occupy a special place or that the universe has a preferred direction forces a radical rethinking of everything we thought we knew. The axis of evil remains one of the most controversial and unresolved issues in cosmology. It is a statistical ghost, not quite strong enough to claim a definitive discovery of new physics, but far too persistent to be comfortably ignored. It serves as a constant, humbling reminder that our map of the universe is still incomplete, and that the cosmos might yet have surprises that defy our most cherished assumptions about its nature and our place within it. If the axis of evil makes our universe feel strangely aware of our place within it, this next mystery does the opposite. It suggests the cosmos might be far smaller and far more finite than we ever imagined. According to our most fundamental theories, the Big Bang should have generated a cacophony of sound waves, ripples in the fabric of space-time that would have left their mark as temperature variations on the cosmic microwave background. We see those ripples, but there's a crucial piece missing. The largest possible waves, the ones that would correspond to the deepest, most fundamental notes in the universe's chord, appear to be silent. The symphony of creation seems to be missing its bass line. This is the mystery of the missing large-scale anisotropies, and it forces us to question the very shape and size of everything that exists. Think of the early universe as a vast musical instrument. The initial burst of energy from the Big Bang sent shockwaves propagating through the hot, dense plasma, much like a ringing bell. These waves, known as Baryon acoustic oscillations, had a maximum possible size they could reach before the universe cooled enough for light to travel freely, a moment we call recombination. That maximum distance acts like the fundamental wavelength of the universe's first sound. When we look at the CMB, we should see the imprint of those monumental waves as temperature variations on the very largest scales. Yet, when we analyze the data from the Planck satellite and other observatories, the power of these fluctuations is significantly weaker than our models predict. It's as if the universe's largest bell was struck, but it only produced a faint, muted thud instead of a deep, resonant gong. One of the most profound explanations for this absence is that the universe might not be infinite. Our standard cosmological models typically assume a universe that stretches on forever, a vast, unbounded expanse. But what if that's not true? What if the cosmos is actually finite in size? If the universe were smaller than the wavelength of those largest possible sound waves, those particular vibrations simply couldn't fit. They would be physically impossible, like trying to fit a wave longer than the entire ocean into a small swimming pool. In a finite universe, there's a natural cutoff. You cannot have a wave larger than the universe itself. This would perfectly explain why we see a drop in power on the largest scales. Those scales literally do not exist. This idea leads us into the fascinating realm of cosmic topology and the possibility that our universe could be multiply connected. Imagine an old-fashioned video game where a spaceship flying off the top of the screen instantly reappears at the bottom. The screen is finite, but it has no true edge. Now apply that concept to our entire reality. A multiply-connected universe means that if you could point a spaceship in one direction and travel in a perfectly straight line for an unimaginably long time, you wouldn't journey forever into nothingness. Instead, you'd eventually return to your starting point like a traveler circumnavigating a globe. The most commonly proposed shape for such a finite universe is a three-dimensional torus, a sort of hyperdonut. In this scenario, the universe isn't infinite. It's just extremely large and wrapped around on itself in a way that hides its true finitude from our local observations. The implications of this for cosmic structure formation are immense. Our entire understanding of how galaxies and galaxy clusters formed is based on the gravitational collapse of those initial density fluctuations imprinted in the CMB. If the largest fluctuations are missing, it means the seeds for the largest structures in the universe are also absent. This could help explain why some of the vast cosmic webs and superclusters we observe seem to stop growing at a certain scale. The models that predict an endless hierarchy of larger and larger structures might be based on an incorrect assumption of an infinite universe. A finite, multiply-connected cosmos would have a built-in maximum size for everything within it, from sound waves to galaxy filaments. Of course, the hunt for evidence of a finite universe is incredibly difficult. It would be like a tiny microbe trying to determine the shape of the entire Earth from its position on a single grain of sand. Scientists search for telltale signs in the CMB, like matching pairs of circles patterns in the background radiation that are identical because they are actually the same region of space, seen from two different directions as the light wraps around the universe. So far, no such conclusive evidence has been found, but the mystery of the missing fluctuations keeps the search alive. It stands as a powerful reminder that our assumptions about the cosmos are just that, assumptions. The universe might be grand, but it may not be endless, and its true topology could be the greatest discovery about reality still waiting to be made. Moving from the grand question of the universe's possible finitude, we encounter a more specific but equally puzzling statistical oddity hidden within the cosmic background, the surprisingly low quadrupole moment. In the symphony of the CMB's temperature fluctuations, scientists assign mathematical terms to describe the notes. The monopole is the average temperature, the dipole is the motion of our solar system through space, and the quadrupole represents the most fundamental, large-scale distortions in the fabric of the cosmos. It's the first true note of the universe's own melody, the largest ripple we can measure, and according to our best models, this note should be loud and clear. Instead, when we listen, it comes through as a faint, almost hesitant whisper, significantly quieter than anyone predicted. This isn't a minor data quirk. It's a fundamental discrepancy that strikes at the heart of our cosmological models. The power spectrum, a graph that charts the strength of these fluctuations against their angular size on the sky, should show a strong peak for the quadrupole. This expectation is baked into the very recipe of the universe as described by the lambda-cold dark matter model. The observed weakness of this signal suggests that the universe is unexpectedly smooth on its very largest scales. It's as if we expected to find massive, rolling ocean swells after a storm, but instead the sea is peculiarly calm. This anomaly forces us to ask whether our understanding of the ingredients and the initial conditions of the universe is somehow incomplete or flawed. One compelling line of inquiry suggests this faint signal could be the echo of a universe that is, in fact, finite and multiply connected, as we just explored. If the cosmos is smaller than the scale of the quadrupole fluctuation, that specific vibration simply wouldn't have the room to form, naturally explaining its suppressed power. It's an elegant solution that ties two mysteries together. However, other theories venture into even more exotic territory. Some cosmologists propose that the low quadrupole could be a signature of pre-Big Bang physics, a fossilized imprint from a contracting phase that preceded our expansion, or from a quantum gravitational era where the very concepts of space and time were different. Others have suggested it might point to a curvature of the universe so slight that our instruments haven't yet detected it, subtly altering the way the largest waves propagated. Yet, the most pragmatic explanation remains the most stubborn one to rule out systematic error. The quadrupole is exceptionally difficult to measure accurately because its signal is so vulnerable to contamination. The primary culprit is our own Milky Way galaxy. The foreground glow of galactic dust and synchrotron radiation from electrons spiraling in magnetic fields can easily mask or mimic the subtle patterns of the primordial quadrupole. While missions like Planck have employed incredibly sophisticated methods to subtract this foreground interference, the process is extraordinarily complex. A tiny misstep in this subtraction, an imperfect model of our galaxy's structure, could artificially suppress the quadrupole signal, creating a phantom mystery where none truly exists. This possibility ensures that cosmologists must tread a careful line between excitement over new physics and rigor in data hygiene. The enduring enigma of the low quadrupole moment serves as a crucial reminder of the challenges inherent in cosmology. We are trying to decipher the faintest whispers from the edge of time, using data that is incredibly delicate and easily influenced by local phenomena. It represents the painstaking frontier of our knowledge, where the line between a revolutionary discovery and a mundane measurement error is vanishingly thin. Whether it ultimately guides us toward a smaller cosmos, new physics, or simply better data analysis, its presence in our models is a humbling and necessary puzzle. Building directly on the puzzling quiet of the quadrupole is another layer of strange coordination that deepens the enigma of the so-called axis of evil. This involves the octupole moment, the next note in the universe's harmonic series, which describes temperature variations on a slightly smaller, but still vast cosmic scale. Independently, both the faint quadrupole and the octupole are curious, but it's their relationship to each other that truly unnerves cosmologists. These two distinct patterns, which should be oriented randomly according to the standard model, show a surprising and statistically significant degree of alignment. Their preferred directions in space are not independent. They seem to be coordinated, as if some unseen hand gently tuned the largest structures in the nascent cosmos to point in a similar direction. This alignment is more than just a curious data point. It's a direct affront to one of the core assumptions used to analyze the cosmos, Gaussianity. Scientists expect the initial seeds of the universe's structure to be random, a Gaussian field of quantum fluctuations blown up to cosmic size by inflation. In such a field, every fluctuation is independent. There should be no conspiracy, no hidden correlations between the largest scales. The quadrupole and octupole should be dancing to entirely different rhythms, not moving in a strangely synchronized way. This coordinated alignment is a form of non-Gaussianity, a statistical anomaly that suggests the initial conditions of the universe were not as simple and random as we've presumed. It hints at a process at work in the first instance of time that created order and correlation where none should exist. One of the more conventional physics-based explanations for this large-scale coordination involves the influence of primordial magnetic fields. Imagine the universe in its first moments being laced with a pervasive, powerful magnetic field that stretched across the entire cosmos. Such a field could have acted as a guiding framework, exerting a force on the charged plasma of the early universe and organizing the largest ripples to align along its field lines. After this magnetic field dissipated, its imprinted directionality would remain frozen into the distribution of matter and energy, explaining the strange alignment we see billions of years later. While we have no direct evidence for such primordial fields, their existence is theoretically possible, and they remain a compelling candidate for solving not just this alignment, but other cosmological puzzles as well. Yet, the most shocking aspect of this alignment is its apparent connection to us. The preferred axis defined by the coordinated quadrupole and octupole doesn't just exist in some arbitrary galactic coordinate system. Disturbingly, it also shows a non-random alignment with the plane of our own solar system. This is the element that truly earns the phenomenon its dramatic moniker, the axis of evil. The probability that the universe's largest structures would, by pure chance, align with the utterly insignificant ecliptic plane of a random star system in a nondescript galaxy is astronomically low. It creates an uncomfortable and almost unscientific scenario. It looks as if the universe is somehow aware of our place within it. This violates the Copernican principle in its most profound form, suggesting not that we are at the center, but that the entire cosmos has a directional property that bizarrely correlates with our local perspective. This forces a deeply uncomfortable choice upon cosmologists. Either this alignment is a catastrophic fluke, a one-in-a-million statistical anomaly that we just happen to observe, or it is a devastating systematic error buried deep within our data processing. Perhaps the meticulous efforts to remove the foreground glow of our own Milky Way galaxy were imperfect, and a faint, structured contamination from local dust or magnetic fields is mimicking a cosmological signal. Teams have hunted for this error for decades, and while minor foreground effects are always present, none have yet been identified as fully sufficient to explain the persistence and strength of this alignment. The third and most revolutionary possibility is that our fundamental models are wrong. The alignment could be a real feature, a clue that the universe has a preferred direction imprinted from its birth, or even evidence of a pre-Big Bang physics that set a fundamental plane for all of existence. The axis of evil remains a thorn in the side of cosmology, a persistent anomaly that refuses to be ignored and continues to challenge our understanding of a truly random and isotropic universe. Now, this discussion of the quadrupole and octupole naturally brings us to the broader and deeply controversial topic known as the low L multipole controversy. The term multipole might sound technical, but it simply refers to these different scales of fluctuation. The L equals 2 for the quadrupole, L equals 3 for the octupole, and so on. The controversy is that these very first, largest scale multipoles are not behaving as our premier model of the universe, lambda cold dark matter, says they should. They are a chorus out of tune, and their discordant notes are forcing a vigorous debate among cosmologists. Are we seeing hints of new, exotic physics, or are we being fooled by the immense challenge of cleaning our cosmic lens? The heart of the problem is a profound statistical tension. According to the standard cosmological model, which has been spectacularly successful at explaining almost every other aspect of the CMB, the fluctuations we see should be random and uncorrelated. The probability that the quadrupole and octupole would display the specific alignments and the unexpectedly low power that we observe is exceedingly small. We're talking about odds that many scientists would consider a definitive discovery in particle physics. In cosmology, however, the situation is far murkier. The signal is faint, the systematics are treacherous, and the stakes for claiming a breakdown of our standard model are incredibly high. This isn't just a minor tweak to a theory, it's a potential crack in its very foundation. This has led to a fascinating divergence within the scientific community. One camp argues passionately that these anomalies are a clear sign that the lambda-CDM model is incomplete. They propose that the explanation must lie in new physics operating in the primordial universe. Perhaps it's evidence of a non-standard form of inflation that left a specific directional imprint. Maybe it's a signature of the universe being fundamentally anisotropic on its largest scales, possessing a subtle preferred direction that we're only now detecting. Some have even ventured that it could be a consequence of our universe colliding with another bubble universe in the multiverse, an event that would violently disrupt the uniformity of the cosmic background in a specific way. These are thrilling, revolutionary ideas, but they remain speculative without a smoking gun. The other, more conservative camp insists that the answer lies not in rewriting the laws of physics, but in perfecting our data analysis. Their argument is one of humility. We are trying to observe the faintest whisper of the ancient universe while sitting inside the roaring engine of our own vibrant galaxy. The process of foreground subtraction is arguably the most difficult part of analyzing the cosmic microwave background. We must meticulously map and remove the emission from dust, gas, and synchrotron radiation within the Milky Way, and even the faint glow of zodiacal light from within our own solar system. Any error in modeling these complex foregrounds, any tiny misestimation of a galactic dust cloud's properties, could easily imprint a false pattern onto the clean CMB map. This camp contends that the alleged anomalies are merely artifacts of an imperfect cleaning process, smudges on our window to the past, not features of the distant landscape itself. The debate is far from settled because the data itself sits in a frustrating gray area. With each new satellite mission, like WMAP and later Planck, the instruments have become more sensitive and the data processing more sophisticated. Yet these low L anomalies have persisted. They have weakened slightly, but they have not disappeared. This stubbornness is what keeps the controversy alive. If it were a simple error, better data should have eliminated it. The fact that it hasn't gone away entirely lends just enough credence to the new physics camp to sustain a vigorous and essential scientific dialogue. It represents the scientific method in its purest form, a tense, careful, and thrilling tug of war between an elegant established theory and stubborn, unexplained data. The outcome will ultimately be decided not by rhetoric, but by even more precise observations from future missions, which will either finally erase these anomalies or confirm them, forcing us to listen to a new and more complex story of how our universe began. But just as we grapple with the strange alignments on the largest scales, another profound asymmetry emerges, one that splits the entire sky in two. This is the mystery of the hemispherical power asymmetry. When cosmologists created the most detailed map of the cosmic microwave background, they made a startling discovery: the universe has a preferred side. The statistical power of the temperature fluctuations, the overall lumpiness, is not the same everywhere. One half of the sky is noticeably more active and varied than the other. It's as if you took a perfectly marbled piece of steak and found that all the fat and flavor were concentrated on just one side. This isn't a subtle effect. It's a clear, measurable variance that cuts directly across the expected uniformity of the cosmos. The standard cosmological model predicts a universe that is, on average, statistically identical in all directions. The hemispherical power asymmetry is a direct and dramatic violation of this principle. The difference isn't in the average temperature itself, but in the amplitude of the variations around that average. In one hemispherical cap of the sky, the hills and valleys of the primordial landscape are more pronounced. The fluctuations are stronger, indicating a region of space that was somehow denser or more energetic at the moment of recombination. This suggests that the seeds for future cosmic structure were not sown evenly. From its very beginning, the universe may have had a lopsided distribution of energy, a fundamental flaw in its initial conditions that has persisted for billions of years. One of the leading theories to explain this asymmetry involves a tweak to our understanding of cosmic inflation. Perhaps the inflationary field that drove the universe's exponential expansion was not perfectly uniform. It could have had a slight gradient, a tiny variation across space that meant inflation ended just a fraction of a second earlier in one part of the universe than in another. This would mean that the region where inflation ended first had a minuscule head start on the process of converting inflationary energy into particles and radiation. That tiny head start could have translated into a measurable difference in the power of the fluctuations we now observe, imprinted across an entire hemisphere of the sky. It would mean that the very mechanism designed to create perfect smoothness actually contained the seed of its own imperfection. Another tantalizing possibility connects this asymmetry to the primordial-gravitational-wave background. These ripples in space-time, theorized to have been generated during inflation, would have interacted with the density fluctuations in the early plasma. If these gravitational waves were themselves distributed unevenly stronger in one direction than another, they could have modulated the apparent power of the temperature fluctuations we see, creating the observed hemispherical difference. Detecting this primordial gravitational wave signal directly is one of the holy grails of cosmology, and its potential link to this asymmetry makes the hunt even more compelling. Perhaps the most mind-bending explanation is that the asymmetry is not a feature of our universe alone, but a sign of its interaction with something else entirely. Some cosmologists have proposed that the gravitational pull of a neighboring universe in a vast multiverse could have literally tugged on our infant cosmos, distorting its energy distribution and creating a permanent directional bias. In this scenario, the hemisphere with higher power might be the side that was closest to this other cosmic bubble, feeling its influence most strongly during those first fleeting moments. While this idea is highly speculative, it illustrates the profound lengths to which scientists must go to explain such a fundamental anomaly. The impact of this discovery on cosmological models is significant. It forces a re-evaluation of the assumption of statistical isotropy that underpins virtually all of our analyses. If the universe has a preferred direction on such a fundamental level, it means our models are missing a key parameter. We can no longer simply average the properties of the entire sky. We must consider the possibility that the constants of nature or the rules of structure formation might vary slightly depending on which direction you look. The hemispherical power asymmetry is more than a curiosity. It is a direct challenge to our picture of a homogeneous and isotropic cosmos, pushing us toward a more complex and nuanced understanding of the universe's first moments. But while these anomalies challenge our models on the largest scales, a more subtle and meticulous hunt is underway in the fine-grained details of the cosmic microwave background's patterns. This search focuses on a statistical property known as Gaussianity. According to the simplest models of inflation, the quantum fluctuations that seeded all structure in the universe should be Gaussian. This is a specific statistical term meaning the fluctuations were completely random and uncorrelated. Imagine the static on an old analog television, a random, featureless snowstorm of white noise where no one pixel has any relationship to its neighbor. That's what the pattern of the primordial universe should look like, pure, random chaos. The intense search for any deviation from this randomness, for any hidden correlations or patterns within the noise, is the pursuit of non-Gaussianity, and what we find, or fail to find, has monumental consequences for our story of inflation. Finding a significant level of non-Gaussianity would be like discovering a hidden signature in that television static, a faint, recurring shape or a subtle coordination between pixels that shouldn't be there. It would be a direct signal that the physics of the very early universe was more complex than our simplest models suggest. Different types of inflationary theories leave behind distinct, fingerprint-like patterns of non-Gaussianity. For instance, the standard single-field model of inflation, where one energy field drives the expansion, predicts a nearly perfect Gaussian signal, a finding that has so far been confirmed by Planck satellite data. This is a huge victory for the simplest theory. However, more complex models, like those involving multiple fields interacting during inflation, can produce specific, detectable non-Gaussian signals. Finding such a signal wouldn't just tweak our model, it would open a window into a much richer and more dynamic inflationary era, revealing a cosmos born from a complex interplay of forces, not a single, simple event. The implications of a detection would extend far beyond just confirming multi-field inflation. Certain patterns of non-Gaussianity could reveal the presence of exotic particles that existed only during inflation, relics from energy scales far beyond what any particle accelerator on Earth could ever hope to reach. They could even provide clues about the elusive quantum nature of gravity itself, as the fluctuations that became the galaxies we see today are believed to have originated from quantum gravitational processes. The absence of strong non-Gaussianity, which is what we primarily see, is just as telling. It tightly constrains the vast landscape of possible inflationary models, effectively ruling out a great many of the more complex and baroque theories that physicists have dreamed up. It tells us that whatever drove inflation, it was an incredibly smooth and simple process, a surprisingly clean event that left behind a very specific, random kind of chaos. This makes the ongoing search a delicate balancing act. On one hand, the lack of a strong signal supports the elegant, minimalistic models that have been so successful. On the other, physicists continue to comb through the data with ever more sophisticated tools, hoping to find the tiniest deviation, the faintest whisper of a correlation that could unlock a deeper layer of reality. It's a search for a needle in a cosmic haystack, but the reward for finding that needle is a completely new understanding of the universe's first and most dramatic moment. And if the search for non-Gaussianity is like looking for a hidden signature in the cosmic static, then the hunt for primordial gravitational waves is the quest for the universe's very first tremor. This is one of the most dramatic chapters in modern cosmology, a story of high stakes, intense rivalry, and a sobering lesson in cosmic humility. It all centers on a specific, elusive pattern imprinted in the cosmic microwave background known as b-mode-polarization. To understand this, we need to rewind to the moment of recombination, when the universe cooled enough for atoms to form and light to travel free. That light didn't just carry a temperature map, it also carried a specific direction or polarization caused by its last interaction with electrons. Most of this polarization is E-modes, a curl-free pattern that acts like a giant fingerprint of the density fluctuations that created it. But theorists predicted there should be another, far fainter signal hidden within it, b-modes. These are a telltale swirling pattern, a curl in the polarization that could not have been created by simple density variations. Instead, they would be the unique signature of something far more profound, ripples in the very fabric of spacetime itself, generated in the first unimaginable fraction of a second after the Big Bang. These ripples are primordial gravitational waves, theorized to have been produced during the violent, exponential expansion of cosmic inflation. Detecting their imprint would be the ultimate smoking gun for inflation, providing direct, incontrovertible evidence that this incredible event actually happened. Even more importantly, the amplitude of these waves would tell us the energy scale at which inflation occurred. It would be our first direct window into physics at energies a trillion times higher than what the Large Hadron Collider can reach, offering a glimpse of the realm where gravity and quantum mechanics must finally unite. The pursuit of this signal reached a fever pitch in 2014 with the BICEP-2 experiment, a powerful telescope located at the South Pole where the cold, dry air is ideal for observing the faint microwave sky. The team announced a historic discovery. They had found the b-mode-polarization pattern. The scientific world and the media erupted with excitement. It was hailed as a definitive confirmation of inflation and a discovery worthy of a Nobel Prize. The data seemed clear and the implications were staggering, but the celebration was short-lived. A crucial complication had been looming in the background all along: galactic dust. Our own Milky Way is filled with microscopic grains of dust that, when aligned by magnetic fields, can also emit polarized light, a foreground signal that can perfectly mimic the swirling pattern of primordial B-modes. The BICEP-2 team had used a preliminary model of this dust contamination to subtract it from their signal, but the full, high-precision data from the Planck satellite, which had mapped this dust across the entire sky, was not yet available. When the Planck data was finally released and cross-analyzed, the story collapsed. The alleged signal from the dawn of time was almost entirely due to this mundane, local interference. It was a sobering moment for cosmology, a stark reminder of the immense challenge of separating the cosmic signal from the galactic noise. The aftermath of this event led to an unprecedented collaboration between former rivals. The BICEP and Planck teams joined forces, combining their data to create a much more robust, cleaned map of the sky. This joint analysis significantly tightened the limits on what could be detected, pushing the possible amplitude of primordial gravitational waves even lower. The dream of an easy, definitive detection vanished, replaced by the grueling reality of a much longer, more difficult hunt. So where does that leave us today? The search is far from over. A new generation of incredibly sensitive experiments is now underway, each more sophisticated than the last. Projects like the Simons Observatory and the Future Light Bird satellite are being designed with the lessons of BICEP-2 hardwired into their DNA. They will observe at multiple frequencies simultaneously, allowing them to characterize and subtract the polarizing dust with a precision that was previously impossible. They are peering deeper into the sky with more detectors, hunting for a signal that we now know is whisper quiet. What would a definitive detection mean? It would be one of the greatest discoveries in the history of science. It wouldn't just confirm inflation. It would tell us that inflation was driven by an incredibly powerful energy field, pointing the way toward a deeper theory of particle physics. A null result, on the other hand, a failure to detect these waves after an exhaustive search, would be equally profound. It would force us to rule out a wide class of the simplest and most popular inflationary models, sending theorists back to the drawing board to conceive of more exotic alternatives for how our universe began. The quest for B-modes is more than a technical challenge. It is a fundamental inquiry into the nature of reality, a direct line back to the very first moment of everything, and a testament to our relentless drive to understand it. This journey from the first light to the glow of reionization brings us to our next great puzzle, one that hinges on a single, crucial number: the reionization optical depth. This value, often denoted by the Greek letter tau, represents a fundamental chapter in cosmic history. It tells us how much the earliest starlight scrambled the atoms of the universe, and a surprising disagreement over its exact value is forcing us to rewrite the story of the very first galaxies. Think of the universe after it cooled from the Big Bang and became neutral and dark. For hundreds of millions of years, it was a vast, silent sea of hydrogen gas waiting. Then the first stars and galaxies began to flicker on. their intense, energetic ultraviolet radiation began to rip electrons away from those neutral hydrogen atoms, reionizing the gas and slowly burning away the cosmic fog. The optical depth, tau, quantifies how effective this process was. It essentially measures how much this newly freed electrons scattered the light of the cosmic microwave background as it traveled for billions of years to reach us. A higher tau means reionization was a more significant and perhaps earlier event. Here's where the mystery unfolds. Scientists have two primary ways to measure this key number. The first is by analyzing the large-scale polarization patterns in the CMB itself, most notably from the Planck satellite. When those first free electrons began to scatter the CMB photons, they imprinted a specific, large-angle pattern of polarization onto the background radiation. By meticulously measuring this pattern, the Planck team arrived at a very precise value for the optical depth. The second method uses a completely different set of clues. We can directly observe the most distant quasars and galaxies we can find. By studying how the light from these ancient objects is absorbed by the neutral hydrogen gas that still remained along their line of sight, we can piece together a timeline for when the fog finally cleared. The problem is that these two methods are telling us two slightly different stories. The Planck measurement suggests a relatively low optical depth, which points to a later and more rapid reionization process. In this timeline, the universe remained mostly neutral for a long time, and the process of lighting it up didn't really kick into high gear until the universe was around 400 or 500 million years old. However, observations from the Hubble Space Telescope and other instruments are now finding an astonishing number of very bright, very active galaxies at incredibly early times, some when the universe was only 300 million years old. These galaxies are so numerous and so powerful that they could have easily driven a much earlier onset of reionization, which would require a higher optical depth to account for it. The data from these early galaxies seems to be in tension with the story told by the Planck satellite. This discrepancy forces us to confront some fascinating possibilities about the dawn of cosmic structure. One idea is that our inventory of the first stars and galaxies is still incomplete. Perhaps the very first stars, known as population 3 stars, were unimaginably massive and brilliant, burning furiously and dying young in supernova that flooded the early cosmos with ionizing radiation far more efficiently than any star we see today. If these stellar behemoths were common, they could have started the reionization process much earlier than the galaxies we can currently observe, helping to bridge the gap between the two measurements. Alternatively, the issue might not be with the stars themselves, but with how their light escaped into the wider universe. The first galaxies were likely messy, dusty, and gas-rich places. It's possible that a great deal of the ionizing radiation produced by the first stars was immediately absorbed by the dense gas clouds within their own galaxies, never getting the chance to contribute to the large-scale reionization of the intergalactic medium. If our models overestimate how efficiently this light escaped, we would similarly overestimate how quickly these galaxies could have cleared the cosmic fog. The truth might require a more complex model where faint, small galaxies that are currently below our detection threshold played a much larger role than the brilliant beacons we can see. The resolution of this mystery holds the key to understanding one of the most important transitions in cosmic history. The timeline of reionization dictates when the universe became truly transparent, setting the stage for the unfettered growth of galaxies that followed. A later reionization suggests a more sedate and orderly dawn of light, while an earlier one hints at a far more dramatic and explosive birth for the first structures. This isn't just about reconciling two numbers, it's about accurately chronicling the end of the universe's dark ages and the triumphant ignition of the first cosmic dawn. Yet this journey from the primordial universe to our local cosmic neighborhood reveals one of the most heated and consequential debates in modern cosmology, the Hubble constant tension. This isn't just a minor discrepancy between two sets of data. It's a fundamental crack in our understanding of cosmic evolution, and the cosmic microwave background sits right at the heart of it. The Hubble constant, known as H0, is arguably the most important number in cosmology. It tells us the current rate of the universe's expansion, the speed at which galaxies are receding from us. Knowing this value allows us to calculate the age of the universe, trace its history, and predict its ultimate fate. For decades, astronomers have worked to pin down this number with ever greater precision. But now, we find ourselves in a crisis. Two powerful, independent methods of measuring H0 are yielding stubbornly different answers, and the gap between them is not shrinking with better data, it's growing. On one side of this divide, we have the local universe measurements. Astronomers use what's known as the cosmic distance ladder, a meticulous step-by-step process that builds out from our own solar system. They observe pulsating stars called Cepheid variables and cataclysmic stellar explosions known as Type 1, a supernova. These objects are standard candles, meaning we know their intrinsic brightness. By measuring how dim they appear to us, we can calculate their distance with remarkable accuracy. When you combine this distance with measurements of how fast the object is moving away from us, its redshift, you can directly calculate the Hubble constant. This local method, championed by teams like the one using the Hubble Space Telescope, gives us a consistently high value for the expansion rate. On the other side stands the cosmic microwave background, which provides a view from the very beginning of the universe. Satellite missions like Planck don't measure the current expansion rate directly. Instead, they measure the conditions of the infant universe, the precise patterns of hot and cold spots in the CMB. We then take these pristine initial conditions and use our ultra-precise supercomputer models of cosmic evolution, based on the standard lambda cold dark matter model, to essentially hit play and fast-forward the universe 13.8 billion years. The model tells us exactly what the expansion rate should be today, given what the universe looked like at the start. This method yields a value for the Hubble constant that is significantly lower than the one we get from looking at the local universe. The problem is that these two methods are both exquisitely precise, but they are profoundly inaccurate with respect to each other. The local measurement and the CMB inferred prediction disagree by about 4.5 to 5.5 kilometers per second per megaparsec. While that might sound like a small number, the statistical significance of this gap is enormous, sitting at around 5 sigma. In particle physics, that would be celebrated as a definitive discovery of a new phenomenon. In cosmology, it's a glaring paradox. It suggests a very uncomfortable possibility that our standard model of cosmology, which has been incredibly successful at explaining so much, might be missing a crucial piece of physics. This is where the real detective work begins. Cosmologists are now exploring a fascinating array of potential solutions, each more intriguing than the last. One compelling idea is that dark energy, the mysterious force accelerating the expansion of the universe, is not a constant as we've assumed. Perhaps it's dynamic, evolving over time. Maybe it was weaker in the past and has grown stronger, which could explain why the universe is expanding faster now than our model, which assumes a constant dark energy predicts. This would mean our cosmic fate is even more uncertain than we thought. Another possibility involves the ghostly realm of neutrinos and other relativistic particles. The standard model assumes 3 types of neutrinos, but what if there are additional, sterile neutrinos or other unknown lightweight particles that flooded the early universe? These extra-relativistic species would have influenced how fast sound waves traveled in the primordial plasma, subtly altering the size of the frozen ripples we see in the CMB. This would change how we interpret that data, potentially reconciling the early universe's prediction with the local measurement. It would mean the universe's particle content is richer than we currently know. Other theorists are looking at the possibility that dark matter, the invisible scaffolding of the cosmos, has properties beyond simply being cold and collisionless. Perhaps dark matter interacts with itself or with dark energy in ways we haven't accounted for, subtly changing the timeline of structure formation and expansion. Or the solution could be something even more radical, like a slight curvature to the universe that we haven't detected, or a fundamental error in our understanding of gravity itself on cosmic scales. Each proposed solution is a potential revolution in waiting, a clue that the cosmos is far more complex and wondrous than our current theories allow. The Hubble constant tension is more than an academic debate. It's a direct challenge to our comprehension of reality. It forces us to question the very tools and assumptions we use to read the history of the universe. Whether the resolution comes from revising our understanding of dark energy, discovering new particles, or something entirely unforeseen, this discrepancy promises to be the key that unlocks the next great leap in our cosmic understanding. And while the Hubble constant tension forces us to question the forces driving the universe apart, it's the silent, invisible components of the cosmos that may hold the key. We've been talking about dark energy and dark matter as two separate, mysterious entities, one an energy-infusing empty space that drives expansion, the other an invisible form of matter that provides the gravitational glue for galaxies. But what if they aren't independent actors in the cosmic play? What if they are connected, interacting with each other in ways that leave subtle fingerprints on the cosmic microwave background? This possibility forms our next great mystery, the potential connection between dark matter and dark energy. For decades, our standard cosmological model has treated these two dark components as ships passing in the night. Dark matter clumps together under gravity, pulling structures into being, while dark energy operates uniformly across the vacuum of space, pushing everything apart. They are modeled as two separate terms in Einstein's equations, not talking to each other. But several lingering anomalies in the CMB and large-scale structure have prompted physicists to ask a radical question: what if they are communicating? The idea is known as coupled quintessence or interacting dark energy, and it suggests that dark energy, often thought of as a dynamic field called quintessence, could be exchanging energy with dark matter. This interaction wouldn't be a violent collision. It would be a subtle, continuous transfer that slightly alters how structures form and how the universe expands over billions of years. How could we possibly detect such a ghostly conversation? The evidence would be written in the detailed statistics of the cosmic microwave background and the distribution of galaxies we see today. A coupling between dark energy and dark matter would leave a specific signature on the growth of cosmic structure. Normally, dark matter's gravitational pull is what allows tiny density fluctuations in the early universe to snowball into the vast cosmic web of galaxies and clusters. If dark energy is slowly siphoning energy away from dark matter, this process of growth could be subtly suppressed. The peaks in the CMB's power spectrum, which are exquisitely sensitive to this growth history, would be shifted in a specific way. Furthermore, the apparent scale at which baryon acoustic oscillations froze into the universe could be slightly altered, creating a tension with other measurements, much like the one we see in the Hubble constant. These aren't dramatic, glaring errors in the data. They are subtle whispers, hints that our model's assumption of no interaction might be just a little bit off. The theoretical frameworks for this interaction are as fascinating as they are varied. One compelling model is known as coupled quintessence. In this scenario, dark energy is not a static cosmological constant but a dynamic field that evolves over time. This field could be very weakly coupled to dark matter particles, meaning they can slowly exchange energy. This interaction would cause the strength of dark energy and the mass of dark matter to evolve in tandem across cosmic history. Another, even more radical idea is that dark matter and dark energy aren't two separate things at all, but different manifestations of a single underlying substance, a unified dark fluid. This fluid would have properties that mimic dark matter's clumping behavior in regions of high density, but act like dark energy's repulsive force in the emptiness of space. Such a model would fundamentally rewrite the list of ingredients that make up our universe. Perhaps the most profound implication of this line of thinking is that it might provide an elegant solution to the Hubble constant tension itself. If dark energy and dark matter are interacting, it means the evolution of the universe's expansion rate is not as straightforward as our models assume. The transfer of energy between these two components could mean that dark energy became dominant at a different time or with a different strength than we've calculated. This would change the predicted expansion history from the CMB, potentially bringing it into alignment with the value we measure directly in the local universe. In this way, the Hubble tension might not be a crisis but a clue, the most visible sign that a deeper connection exists in the dark sector of the universe. Of course, the conservative view remains that dark matter and dark energy are indeed separate and non-interacting. The evidence for any coupling is still tentative, hidden in the margins of error of our most precise experiments. But the very fact that such ideas are being seriously pursued by leading cosmologists shows how powerfully anomalies like the Hubble tension are reshaping our frontiers. They force us to consider that the universe's greatest mysteries might not be independent puzzles, but pieces of a larger, more interconnected picture that we are only beginning to glimpse. The search for a connection in the dark is a testament to cosmology's relentless drive to look beyond the standard model, probing the shadows for a more complete theory of everything. But as we contemplate the vast, dark components shaping our cosmos, we must also turn our attention to a far more elusive and ancient sea of particles that floods every corner of the universe, a relic even more pristine than the cosmic microwave background itself. This is the cosmic neutrino background, a whisper from the very first second of creation, and its ghostly influence is subtly imprinted onto the CMB we observe today. While the CMB shows us the universe at 380,000 years old, the neutrino background carries information from a time just 1 second after the Big Bang, making it the oldest fossil in all of cosmology. Neutrinos are among the most enigmatic fundamental particles we know of. They are fantastically abundant. Billions pass through your thumbnail every second, yet they barely interact with anything. They are nature's perfect ghosts. In the searing heat of the very early universe, neutrinos were produced in immense numbers and were constantly interacting with other particles. But as the universe expanded and cooled, roughly 1 second after the Big Bang, it suddenly became too cold and too sparse for these weak interacting particles to find anything to collide with. In an instant, they streamed free, decoupling from the rest of the cosmic plasma and forming a background that has been cooling and stretching with the expansion of the universe ever since. This is the cosmic neutrino background, and while we have not yet detected it directly, its gravitational influence left an indelible mark on the CMB. We can't see this neutrino background with our telescopes, but we can feel its effects. Those trillions of neutrinos streaming through the infant universe were not passive spectators. They had a significant impact on the growth of cosmic structure through their gravity and their unique behavior. Because they were moving at nearly the speed of light when they decoupled, they are what cosmologists call relativistic particles. This means they tend to smooth things out. As tiny density fluctuations in the dark matter and baryons began to gravitationally collapse to form the seeds of galaxies, the neutrinos acted as a counterforce. Their high speeds meant they could easily stream out of these nascent gravitational wells, washing out the very small-scale fluctuations and suppressing the growth of structure. This suppression is a clear and specific signature that we can look for in the detailed power spectrum of the CMB. The Planck satellite's incredibly precise measurements of the CMB's temperature and polarization fluctuations have provided the strongest indirect evidence for this cosmic sea of neutrinos. The data shows a distinct suppression of power on smaller angular scales, exactly as predicted if a specific amount of relativistic energy, the energy of these light, fast-moving neutrinos, was present in the early universe. By analyzing this suppression, cosmologists can not only confirm the existence of the cosmic neutrino background, but also count the number of neutrino species. The Planck results are beautifully consistent with the 3 neutrino types predicted by the standard model of particle physics. This is a stunning achievement, using the afterglow of the Big Bang to confirm a prediction about particles that decoupled a mere second after the universe began. Yet the story doesn't end with mere confirmation. The subtle imprint on the CMB also provides our best estimate of the combined mass of all neutrino species. For a long time, neutrinos were thought to be massless, but we now know from particle physics experiments that they must have a tiny, non-zero mass. The CMB data, combined with measurements of large-scale structure, tells us that the combined mass of the 3 neutrinos is extraordinarily small, certainly less than 0.1 electron volts. This is minuscule. For comparison, a single electron is over 500,000 times more massive. This constraint from cosmology is a powerful cross-check on experiments here on Earth and helps us understand the mysterious mechanism that gives these ghosts their infinitesimal weight. The next great frontier is the direct detection of the cosmic neutrino background itself. Catching one of these primordial neutrinos is arguably one of the most difficult challenges in all of experimental physics. These particles are now incredibly low energy due to the cosmic expansion, with energies equivalent to a temperature of just 1.95 degrees above absolute zero, even colder than the CMB. Detecting them requires unimaginably sensitive instruments that can distinguish these ancient neutrinos from the overwhelming background of neutrinos produced by the Sun, nuclear reactors, and cosmic rays hitting our atmosphere. Proposed experiments aim to use large volumes of ultra-pure solid materials or intense radioactive sources, watching for the impossibly rare occasion when a Big Bang neutrino deposits a minuscule amount of energy. Successfully capturing a direct signal would open a new window into the dawn of time. It would allow us to study the conditions of the universe at 1 second old with a clarity we can only dream of today. It could reveal if there are more than 3 types of neutrinos, such as the hypothesized sterile neutrino, which would have profound implications for particle physics and cosmology. It could also provide an independent, pristine measurement of the neutrino masses, free from the complexities of interpreting the CMB's indirect imprint. The direct detection of the cosmic neutrino background would be a Nobel Prize-winning moment, allowing us to listen to the universe's first breath, a whisper that has traveled for 13.8 billion years, waiting for us to finally hear it. But the influence of those first particles doesn't end with neutrinos. As we peel back the layers of the early universe, we arrive at one of the most captivating and radical ideas in modern cosmology: the possibility that the very first black holes, forged not from dying stars but from the raw energy of the Big Bang itself, could be the invisible dark matter that shapes our cosmos, and their violent birth may have left a hidden scar on the cosmic microwave. Background: this is the primordial black hole hypothesis, a concept that elegantly ties together 2 of our greatest mysteries. Primordial black holes are a theoretical class of objects unlike any black hole we've observed. They are not the end result of a massive star's collapse. Instead, they are thought to have been born in the incredibly dense and turbulent environment of the universe's first second. Imagine the cosmos in its infancy, a seething, hot soup of energy. Within this chaos, random quantum fluctuations could have created tiny regions so dense that their own gravity caused them to directly collapse, bypassing the need for a star entirely. These black holes could have formed with a vast range of masses, from smaller than a pinhead to many times the mass of our Sun. And if they formed in sufficient numbers, they could account for the entire inventory of dark matter, the mysterious substance that makes up over 80% of all matter in the universe. The beauty of this idea lies in its simplicity. It solves two profound problems at once: the nature of dark matter and the origin of the universe's first black holes, which we now see merging in events detected by gravitational wave observatories. But such a radical proposal requires extraordinary evidence, and that's where the cosmic microwave background comes in. The formation of a primordial black hole would have been an incredibly violent event, a sudden and intense concentration of energy. This process would have released a tremendous burst of radiation. If enough of these black holes formed in the first few months after the Big Bang, their collective energy output would have significantly heated the surrounding hydrogen gas. This heating would have left a specific telltale mark on the CMB known as a spectral distortion. The blackbody spectrum of the CMB is famously smooth, a perfect curve. But if the early universe was heated by these eruptions, that energy would have interacted with the plasma, subtly altering this perfect curve, creating specific wiggles or deviations, particularly in the microwave and radio frequencies. Satellites like COBE and Planck have measured this spectrum with exquisite precision, and it is incredibly smooth. This remarkable smoothness places extremely tight constraints on how many primordial black holes could have formed. It effectively rules out the possibility that a large population of very massive or very numerous black holes existed early on, as their cumulative energy injection would have distorted the spectrum in a way we simply do not see. However, the story is far from over. These constraints are mass-dependent. They may rule out a universe filled with Earth mass or asteroid mass primordial black holes, but they leave the door open for other mass ranges. A particularly intriguing window exists for black holes with masses around that of a large asteroid. If these objects were abundant, they could potentially constitute a significant fraction of the dark matter without violating the CMB spectral constraints. Their formation would have been numerous but individually less energetic, creating a subtler collective effect that might still be consistent with the pristine blackbody spectrum we observe. The hunt for evidence now extends beyond the CMB's spectral shape. Cosmologists are also looking at the CMB's polarization and its tiny temperature fluctuations. The gravitational influence of a vast population of primordial black holes would subtly affect how sound waves propagated in the early plasma, potentially leaving a faint signature in the statistical distribution of the hot and cold spots. Furthermore, if these black holes were hurtling through space, their motion could have created additional specific patterns. While no smoking gun has been found, the continued refinement of our CMB maps offers a powerful tool to test this fascinating hypothesis. The implications of a confirmed primordial black hole dark matter scenario would be nothing short of revolutionary. It would mean that the dark matter halos enveloping galaxies are not made of unknown exotic particles, but of ancient black holes, fossils from the very first moment of time. It would provide a natural explanation for the unexpected masses of black holes detected by LIGO and Virgo, suggesting they are not stellar remnants but primordial relics finally finding each other. Most profoundly, it would directly connect the largest structures in the universe today to the most extreme physics of its birth, offering a breathtakingly direct link between the macroscopic cosmos and the quantum fluctuations that spawned it. While the evidence remains elusive, the primordial black hole hypothesis stands as a powerful testament to the creativity of cosmology, using the ancient light of the CMB to probe the darkest and most dramatic possibilities of the cosmic dawn. But the story of the universe's shape is written not just in its expansion but in the very geometry of space itself, a fundamental property we call curvature. This brings us to a mystery that cuts to the core of cosmic architecture. Is the universe flat or is it curved? The answer, which we have largely gleaned from the cosmic microwave background, is both definitive and strangely perplexing, with subtle anomalies that keep the door open to a more complex reality. In the language of Einstein's general relativity, the universe can have three possible geometries dictated by the total density of all its matter and energy. If the density is exactly at a critical value, space is flat, obeying the standard rules of Euclidean geometry we learned in school. Parallel lines never meet, and the angles of a triangle always add up to 180 degrees. If the density is higher than this critical value, the universe has positive curvature, making it a closed sphere. In such a universe, parallel lines would eventually converge, and a giant triangle would have angles summing to more than 180 degrees. If the density is lower, the universe has negative curvature, forming an open, saddle-shaped hyperboloid where parallel lines diverge and triangles have angles adding up to less than 180 degrees. This curvature isn't just a mathematical abstraction. It dictates the universe's ultimate fate and is imprinted on the pattern of the CMB. The primary way we measure this is by using the cosmic microwave background as the ultimate cosmic ruler. Those frozen sound waves, the Barrian acoustic oscillations, have a known physical size. They stretch to about 500,000 light-years across by the time of recombination. We know this scale from our understanding of plasma physics and the speed of sound in the early universe. When we look at the CMB, we measure the angular size of these ripples on the sky, how many degrees they span. In a flat universe, geometry is simple. The angular size we see directly corresponds to the known physical size at that great distance. In a curved universe, this relationship breaks down. Positive curvature would act like a magnifying glass, making the same physical ripples appear larger on the sky. Negative curvature would have the opposite effect, making them appear smaller. When we analyze the data from the Planck satellite, the result is incredibly precise. The universe is flat, or so nearly flat that we cannot measure any deviation. The observed angular size of the fluctuations matches the prediction for a perfectly flat universe with astonishing accuracy. This finding is a monumental triumph for the theory of cosmic inflation, which predicted that the violent exponential expansion would have stretched the fabric of spacetime so dramatically that any initial curvature would have been flattened out, much like inflating a balloon to cosmic proportions makes its surface appear flat to a tiny ant living on it. A flat universe strongly suggests that the total density of the cosmos is exactly at the critical value, a finding that neatly dovetails with our inventory of dark matter and dark energy. However, so nearly flat is a phrase that contains a universe of possibility. Despite the overwhelming evidence for flatness, there remain intriguing, subtle hints in the Planck data that suggest the possibility of a slight positive curvature, a universe that is ever so gently closed. This evidence sits at the very edge of statistical significance, not enough to claim a discovery but too persistent to ignore completely. It manifests as a slight enhancement of the gravitational lensing effect observed in the CMB, which seems a bit stronger than the standard flat model predicts. If real, this would mean the universe's density is slightly higher than the critical value, and the geometry of all reality is a vast, gently curved hypersphere. The implications of even a tiny deviation from perfect flatness are profound. For inflationary theory, it would demand an explanation. Why would inflation have stopped just short of completely flattening the universe? It would require a specific and slightly different inflationary potential, pointing toward a more complex model than the simplest versions. For the ultimate fate of the cosmos, a positively curved universe would eventually stop expanding and collapse back in on itself in a big crunch, a fiery end to match its fiery beginning. While dark energy currently dominates and drives acceleration, a closed universe means this acceleration might not last forever. Gravity would ultimately win. This tantalizing hint of curvature remains one of the most carefully watched anomalies in cosmology. Future experiments like next-generation CMB observatories will measure the polarization and lensing of the ancient light with even greater precision, hoping to definitively confirm or rule out this ghost of a curve. Whether the universe is perfectly flat or infinitesimally curved, the answer will force us to refine our understanding of its birth and its destiny, reminding us that even in a seemingly settled question, the cosmos may yet hold a final, surprising twist. This brings us to a moment in cosmic history so pivotal that it literally made the universe visible, an event whose precise timing is encoded in the very spectrum of the light we study. We call this moment recombination, and while the name might sound like a simple reconnection, the process was anything but. It represents the point when the hot, opaque fog of the primordial plasma cooled enough for electrons to finally be captured by protons, forming the first stable hydrogen atoms and releasing the cosmic microwave background in a brilliant flash across the entire cosmos. But this transition wasn't an instantaneous, universe-wide flip of a switch. It was a delicate dance of probability that unfolded over tens of thousands of years, and the subtle details of its timing hold crucial clues to the universe's earliest chemical composition. To truly appreciate this, we need to step back into that searing early universe. For its first several 100,000 years, it was far too hot for atoms to exist. Space was filled with a thick, roiling plasma of completely ionized matter, a soup of bare atomic nuclei and free electrons, all constantly bombarded by photons of light. These photons couldn't travel more than a tiny fraction of an inch before scattering off a free electron, effectively trapped in a relentless game of pinball. The universe was, for all intents and purposes, opaque, a brilliant but impenetrable fog. But as expansion continued, everything cooled. The average energy of the photons gradually dropped below the energy needed to keep electrons kicked free from protons. It was at this critical juncture that the path of the universe forked. Recombination wasn't a simple, one-step capture. It was a statistical process governed by an intricate balance between the rate of expansion, the density of particles, and the probability of capture. Think of it like a crowded room where everyone is trying to find a partner to dance with, but the music is still so loud that it keeps breaking them apart. As the music slowly fades, more and more couples can stick together. In the cosmic sense, protons and electrons began to form hydrogen atoms, but the few remaining high-energy photons could still immediately rip them apart again. The universe didn't become transparent all at once. It slowly cleared over a span of approximately 60,000 years, a period known as the photon decoupling era. The CMB we see is a snapshot of that entire process, with the peak of this transition happening when the universe was about 380,000 years old. The precise details of this timeline are not just academic, they are directly imprinted onto the blackbody spectrum of the CMB itself. The moment when photons scattered for the last time depended critically on the number of free electrons available. If there were more electrons, the fog would have taken slightly longer to clear. If there were fewer, it would have happened a bit sooner. This is where the primordial element abundances become the critical variable. The vast majority of those free electrons came from hydrogen, the simplest element, but the universe also cooked up a small amount of helium and an even tinier trace of lithium in its first few minutes during Big Bang nucleosynthesis. This is crucial because helium atoms are structured differently. A helium nucleus has two protons, meaning it holds onto its two electrons much more tightly than a single proton can hold onto one. Helium actually recombined earlier than hydrogen, effectively taking its electrons off the playing field sooner. Therefore, the exact amount of helium produced in the Big Bang directly influenced the timeline of hydrogen recombination. A higher primordial helium abundance would mean fewer free electrons were available to scatter light when the temperature fell to the point where hydrogen could finally form. This would have allowed photons to travel free just a little bit earlier. This tiny shift in the timing of the universe's transition from opaque to transparent would leave a subtle but measurable signature. It would slightly alter the precise shape of the CMB's perfect blackbody spectrum, and would also modify the relative amplitudes of the peaks and troughs in the temperature fluctuation power spectrum. By measuring these minute effects with exquisite precision, missions like Planck have been able to indirectly measure the abundance of helium from the Big Bang, and the results are a stunning confirmation of our models. The observed CMB data points to a helium fraction of about 24% by mass, which matches almost perfectly the predictions from Big Bang nucleosynthesis calculations. This incredible agreement is a triumph for the standard model of cosmology, but it also opens a new frontier for precision tests. As our measurements become even more sensitive, any tiny deviation in the inferred helium abundance from the CMB versus the value we get from observing ancient, pristine gas clouds in distant galaxies could signal new physics. It could hint at the existence of previously unknown particles, like additional types of neutrinos, that were present during nucleosynthesis and subtly altered the nuclear reaction rates that determined how much helium was forged. The timing of recombination, a seemingly straightforward event, is therefore a powerful chronometer and a chemical probe. It connects the physics of the universe at 380,000 years old directly back to its conditions at just 1 minute old, allowing us to use the afterglow of the first light to weigh the ingredients of the first elements. But if the precise timing of recombination gave us a window into the universe's first elements, the quest to measure the absolute purity of the cosmic microwave background spectrum takes us even deeper into realms of energy so extreme they defy imagination. We've spoken of the CMB's blackbody curve as being miraculously smooth, a perfect thermal echo. Yet, cosmologists are engaged in a painstaking hunt for the tiniest imperfections in that spectral perfection, deviations so minute they haven't yet been definitively found. These hypothetical spectral distortions are like cosmic hieroglyphs, and if we can learn to read them, they would tell us stories of the universe's very first femtosecond, a period completely inaccessible by any other means. The concept hinges on a beautiful piece of physics. In the very early universe, the incredibly dense plasma was in a state of perfect thermal equilibrium. The particles and photons were constantly colliding, efficiently sharing energy and maintaining a perfect blackbody spectrum, a smooth curve defined only by the temperature. This is the spectrum we largely see today. However, this perfection can be disrupted if a significant amount of energy is dumped into the cosmic plasma at a specific time. Depending on when this energy injection happens, it creates a specific type of fingerprint on the spectrum, known as either a mu distortion or a Y distortion. These aren't blobs on a map, they are subtle shifts in the intensity of light at specific wavelengths, a slight hump or dip on the side of that perfect curve. A Y distortion, named after the Y parameter used to describe it, is the signature of a relatively late energy injection, occurring between about 1,000 and 1 million years after the Big Bang. By this time, the universe has expanded and cooled enough that photons and electrons are no longer colliding frequently enough to maintain perfect thermal equilibrium instantly. If a burst of energy heats the electrons at this epoch, through a process called Compton, scattering the electrons then impart this energy to the photons, but inefficiently. This creates a specific distortion where the spectrum appears to have more high-energy photons and fewer low-energy photons than a perfect blackbody should. It's like slightly stretching the high-energy end of the curve. This kind of signal could be a telltale sign of the first generations of stars and galaxies beginning to heat the intergalactic gas, or even the dissipation of primordial magnetic fields or cosmic strings. The mu distortion, or mu distortion, is the real prize for probing the truly ancient universe. This signal is created by energy injections that happened incredibly early, between just a few months and about 300,000 years after the Big Bang. During this narrow window, the universe was still dense enough for photons and electrons to collide frequently, but a specific process called double Compton scattering, which is efficient at creating new photons to restore the perfect spectrum, had become ineffective. If energy was released in this era, it would get thermalized, but not perfectly. Instead of creating a new, hotter blackbody curve, it would create a specific chemical potential-like distortion, a mu distortion. This is the key. A mu distortion is a fossil permanently frozen into the light from events that occurred long before the CMB itself was released. What could possibly have caused such energy injections in the infant cosmos? The possibilities are as thrilling as they are varied. One of the most compelling is the annihilation or decay of exotic, hypothetical particles that existed only in the universe's first moments. Imagine a population of heavy, long-lived particles, relics from a grand unified theory of physics, finally decaying away and flooding the cosmos with radiation. That burst of energy would leave a mu distortion in its wake. Alternatively, the dissipation of sound waves from a more complex period of inflation, or even the evaporation of those primordial black holes we discussed earlier, could have deposited immense energy into the plasma. Each different source would create a distortion with a slightly different spectral shape, meaning that if we could detect it, we wouldn't just know that something happened. We could potentially identify exactly what that something was. The search for these distortions represents one of the most technically ambitious frontiers in observational cosmology. We are not just mapping temperature, we are measuring the spectrum of the CMB across the entire sky with a precision of 1 part in a billion. Satellites like COBE and Planck have confirmed the incredible blackbody nature of the CMB, but they were not sensitive enough to detect the minuscule deviations predicted by many theories. The next generation of missions, such as the proposed PIXI spectrometer, are designed specifically for this hunt. They aim to measure the sky's spectrum with such exquisite accuracy that the ghostly imprints of the universe's most violent early moments would finally come into view. Finding a spectral distortion would be like discovering a new, entirely different chapter of the cosmic biography, written in the faintest ink on the oldest light. It would provide direct, empirical evidence for physics at energy scales 1 billion times higher than what we can probe in particle colliders, offering a unique glimpse into the forces that shaped reality itself. The perfect blackbody spectrum is a testament to the universe's smooth beginning, but it is the search for its tiny, hidden imperfections that may ultimately reveal its most dramatic and explosive secrets. And as we delve deeper into the map of the primordial universe, we find patterns that seem to whisper of an order beyond randomness, a choreography written into the fabric of space-time itself. This is the mystery of the aligned spots and strange correlations, where the cold and hot patches of the cosmic microwave background appear to be talking to each other across vast distances, defying the simple explanation of random chance and pointing toward physics that might operate on a canvas far larger than our observable universe. When scientists analyze the CMB, they don't just look at the temperature variations, they search for hidden relationships between them. They ask whether the arrangement of hot and cold spots is truly as random as the standard inflationary model demands, or if there are subtle correlations, unexpected handshakes between regions that should be complete strangers. Several independent studies have suggested that the latter might be true. Certain large cold spots and hot spots seem to be aligned along specific, preferred axes or arranged in patterns that exhibit a strange kind of symmetry. It's as if you tossed a handful of confetti into the air and it somehow landed to spell out a word. The probability is so low that you're forced to consider that it wasn't a random throw at all. One of the most discussed proposals to explain these correlations is the concept of a cyclic universe. In this breathtaking model, the Big Bang was not the absolute beginning but merely the latest in an endless series of expansions and contractions, a cosmic heartbeat echoing across eternity. In this scenario, each previous aeon or cycle leaves a faint imprint on the next. The collisions of supermassive black holes from a previous cycle, or the gravitational waves they generated, could have created specific, large-scale patterns that were then stretched across the sky by the subsequent expansion, creating correlated structures in the CMB of our own cycle. These aligned spots could therefore be cosmic fossils, scars from a universe that existed before our own, offering us a glimpse into a history that stretches back trillions of years. Alternatively, these strange correlations could be the signatures of cosmic defects, remnants of phase transitions in the early universe. As the cosmos cooled from its unimaginably hot beginning, the fundamental forces of nature are thought to have separated out, much like water freezing into ice. These phase transitions could have created topological defects, one-dimensional cosmic strings, or two-dimensional domain walls, structures of immense energy that would have woven through the fabric of space-time. The gravitational influence of such a vast cosmic string, for instance, could have created a sharp, linear feature in the CMB, a clear line of correlated cold spots in its wake. While we have yet to find direct evidence for these exotic structures, their predicted imprints provide a compelling explanation for the kind of large-scale, coordinated patterns that seem to challenge a purely random origin. Of course, the most conservative explanation remains that these alignments are simply statistical flukes, the inevitable result of scanning a massive dataset for any pattern, no matter how improbable. In any truly random map, there will always be some spots that, by sheer chance, appear to line up. The challenge for cosmologists is to determine the precise threshold where coincidence ends and physics begins. This is a delicate balancing act, requiring ever more sophisticated statistical tools to distinguish a real signal from the background noise of a complex cosmos. With each new analysis, the anomalies sometimes weaken, but they rarely vanish entirely, maintaining a tantalizing foothold on the edge of discovery. Whether these aligned spots are ghosts of a previous cosmic cycle, the tangled threads of cosmic strings, or simply a magnificent illusion of statistics, their continued presence in our data serves as a vital catalyst for questioning our most fundamental assumptions. They push us to consider models of the universe that are far grander and more complex than the simple story of a single, isolated Big Bang, inviting us to ponder a cosmos of breathtaking cycles and structures that transcend the horizon of our own existence. Now we venture into the realm of the truly exotic, where the fabric of spacetime itself might be frayed, knotted, and woven with unimaginably dense filaments left over from the universe's fiery birth. This is the mystery of cosmic strings, hypothetical one-dimensional scars in the cosmos whose ghostly pull could have written its signature into the ancient light we observe today. To understand what a cosmic string is, we need to journey back to a time of unimaginable energy, mere fractions of a second after the Big Bang. As the universe expanded and cooled, the fundamental forces that govern reality are believed to have undergone phase transitions, separating from a unified superforce into the distinct interactions we know today: gravity, electromagnetism, and the strong and weak nuclear forces. Think of it like water freezing into ice. When water freezes, its symmetrical liquid state breaks, and imperfections like cracks can form in the ice. In a similar way, as the universe's underlying quantum fields cooled and settled into their current state, their symmetry could have broken in an imperfect way, giving rise to topological defects. Cosmic strings are one such possible defect. They are not strings made of any material substance. They are incredibly thin, unimaginably dense wrinkles in the very fabric of spacetime itself, thinner than a proton but with the mass of a mountain range packed into every inch of their length. They would be under immense tension, and their gravitational influence would be profound. The presence of such a string stretching across the universe would warp the space around it in a unique way. Because it is a one-dimensional object with tremendous mass, it creates a gravitational field that is qualitatively different from that of a star or a planet. Space around a cosmic string is conformally flat, meaning it doesn't exert a traditional attractive pull. Instead, it creates a deficit angle in spacetime. Imagine you're walking in a complete circle around a cosmic string. Normally, circling an object would bring you back to your starting point after 360 degrees. But because of the way the string warps space, you would actually end up a few degrees short of a full circle. This bizarre geometry has a startling consequence. It would act as a gravitational lens, but one that creates identical, duplicate images of objects located behind it. If a cosmic string passed between us and a distant galaxy, we might see two perfect, identical copies of that galaxy side by side in the sky. So, how would these bizarre objects leave their mark on the cosmic microwave background? Their primary influence would be through a phenomenon called the Kaiser-Stebbins effect. As a cosmic string moves through the universe at a significant fraction of the speed of light, it shears the spacetime behind it. This shear would create a velocity kick for any particles or photons on one side of the string relative to the other. For the CMB, this would manifest as a very specific, very sharp discontinuity in temperature. Imagine a line drawn across the sky where on one side the ancient light is very slightly hotter, and on the other side it is very slightly colder. This would not be a smooth, gradual gradient but an instantaneous step-like jump in temperature. This is a unique fingerprint that would be incredibly difficult to explain by any other known physical process. Beyond temperature, cosmic strings would also impart a distinct pattern on the polarization of the CMB. Their immense gravitational influence would generate vector and tensor perturbations, specific types of distortions that could produce a unique swirling pattern, or b-mode polarization, that is different from the pattern created by primordial-gravitational-waves. Finding such a specific polarization signature, especially if it were aligned with a linear temperature discontinuity, would be a powerful indicator of a cosmic string's existence. The detection of even a single cosmic string would be nothing short of revolutionary. It would provide direct, observational evidence for the grand unified theories of particle physics, offering a tangible glimpse into the energy scales and symmetry-breaking processes that occurred when the universe was less than a second old. It would confirm that the cosmos underwent these dramatic phase transitions, validating a key prediction of modern theoretical physics. Furthermore, because cosmic strings would have formed a network that evolved over time, their gravitational interactions could have acted as seeds for the formation of the very first large-scale structures, providing an alternative or complementary mechanism to the quantum fluctuations from inflation. Finding their imprint would mean that the blueprint for galaxies, clusters, and the entire cosmic web was not drawn by one hand alone, but was a collaborative effort between the quantum noise of inflation and the macroscopic scars of the universe's own violent transition into its current state. The hunt for these spacetime scars continues, a search for the faintest of lines that could redraw our entire understanding of cosmic history. Now, as we grapple with the profound implications of the Hubble tension, a fascinating and elegant solution has emerged from the theoretical shadows, proposing that the dark energy we observe today wasn't the only actor on the cosmic stage. What if, in the universe's adolescence, a temporary form of this mysterious force briefly flared into existence, subtly altering the cosmos's expansion history just before the first light was set free? This is the compelling premise of early dark energy, a theoretical tweak that could resolve our most pressing cosmological crisis by modifying a single, crucial cosmic measuring stick. To understand how this works, we need to return to the most important ruler in cosmology, the sound horizon scale. This is the fixed distance that a pressure wave could travel through the hot plasma of the early universe from the Big Bang until the moment of recombination, when the cosmos became transparent. That distance became frozen into the fabric of the universe, imprinting itself as a preferred scale in the distribution of galaxies, and most importantly, as a series of peaks in the power spectrum of the cosmic microwave background. We can measure the angular size of this standard ruler on the sky with incredible precision. From that measurement and our understanding of the physics of the early universe, we infer the physical size of the sound horizon. This is the crucial step. That known physical size is then used as a calibrator to measure distances across the universe, which in turn allows us to calculate the expansion rate, the Hubble constant. The tension arises because when we use this early universe calibrator, we get a different answer for h0 than when we use the local universe's distance ladder. Early dark energy proposes a brilliantly simple fix. What if that sound horizon ruler isn't as fixed as we think? The theory suggests that a new, temporary form of dark energy briefly became significant around the time of recombination, when the universe was a few 100,000 years old. This isn't the dark energy we see today. It's an additional component, a field that would have injected an extra burst of repulsive force into the cosmos for a short period. This extra push would have caused the universe to expand just a little bit faster during that critical epoch. If the expansion rate was slightly higher just before recombination, then the pressure waves in the plasma would have had less time to travel before the music stopped and the waves froze. The result, the sound horizon, our cosmic standard ruler, would be physically smaller than our standard models assume. This is the key insight. All of our measurements that rely on the early universe, including the CMB inferred Hubble constant, are predicated on a specific, calculated size for that ruler. If early dark energy made the ruler smaller, it changes everything. When we look at the CMB and measure the angular size of the sound horizon, a smaller physical ruler would mean that the distance to the CMB is actually closer than we previously calculated. A shorter distance to the CMB implies a faster expansion rate to get us to that point in 13.8 billion years. Suddenly, the Hubble constant derived from the early universe would jump up, potentially aligning it perfectly with the higher value measured by the local distance ladder. In one stroke, this model could reconcile the two conflicting measurements by identifying a single, tweakable parameter in the cosmic recipe that affects the calibrator itself. The beauty of this idea is that it leaves a specific, testable fingerprint on the cosmic microwave background. By altering the expansion history right before recombination, early dark energy would slightly modify the relative heights and positions of the acoustic peaks in the CMB power spectrum. The models that best fit the data suggest this early dark energy would have contributed a few percent to the total energy density of the universe at its peak, before fading away rapidly and becoming negligible thereafter. This is just enough to shrink the sound horizon by the required amount without completely destroying the otherwise excellent fit of the standard model to the vast array of other cosmological data. It's a surgical intervention, a subtle adjustment to the universe's adolescence that fixes a problem in its adulthood. Of course, such a radical proposal is not without its own profound questions. What is the physical nature of this early dark energy? Is it a fundamental scalar field similar to the inflaton that powered the universe's birth? If so, why did it activate only during that specific window of time? How did it couple to the rest of the components in the universe? Furthermore, while it elegantly solves the Hubble tension, it must also be checked against a host of other constraints, from the observed large-scale structure of the universe to the precise details of Big Bang nucleosynthesis. The model walks a fine line, offering a compelling solution while demanding a new, exotic particle or field for which we currently have no other direct evidence. The search for this evidence is now a driving force in cosmology, pushing us to refine our measurements of the CMB's detailed structure to either confirm the subtle signatures of this transient force or finally rule it out, closing one of the most promising chapters in our quest to understand why the universe's expansion rate remains such a deeply puzzling mystery. Now, while we've been exploring the grandest scales of the universe, from its overall curvature to the possibility of cosmic strings, there's a fundamental feature of the cosmic microwave background that is both the most obvious and the most thoroughly measured. Yet it holds its own subtle mysteries that connect directly to our place in the cosmos. This is the CMB dipole, and it's the first and largest anisotropy or directional difference that any experiment detects when it points at the sky. At first glance, its explanation seems simple. It's the unmistakable signature of our own motion. But like so much in cosmology, the closer we look, the more intriguing this simple story becomes. Imagine you're standing in a gentle snowfall. If you stand still, the snowflakes appear to fall straight down around you. But if you start to run forward, you'll see the flakes coming at you from a direction slightly ahead. It will seem like the snow is falling toward you from the front. This is the Doppler effect in action. Now, apply that to the entire universe. The CMB fills all of space like a bath of radiation with a near-perfect uniform temperature of 2.725 degrees above absolute zero. But because our solar system is moving at a tremendous speed through space, we don't see this radiation as perfectly uniform. The light coming from the direction we're moving toward appears slightly compressed or blue-shifted, making that part of the sky look a tiny bit warmer. The light from the direction we're moving away from appears stretched or redshifted, making that part of the sky look a tiny bit colder. This creates a dipole pattern, a hot pole in one direction, a cold pole in the exact opposite direction, and a smooth gradient between them. The measurement of this effect is breathtakingly precise. Data from satellites like COBE, WMAP, and Planck show that our solar system is hurtling through space at about 370 kilometers per second relative to this primordial rest frame. That's an astonishing 1.3 million kilometers per hour. The direction of this motion is toward the constellation Leo, a point in the sky known as the apex. This isn't just our sun's motion around the Milky Way. This is the combined velocity of our entire local group of galaxies as it's pulled by the gravitational titans of the cosmos. This measurement is one of the most direct and powerful confirmations that there is no special, privileged frame of reference in the universe. The CBM provides the ultimate backdrop against which all motion can be measured. However, this seemingly straightforward story gets more complex when we try to account for every last bit of that motion. We can add up all the known gravitational pulls acting on us. The primary tug comes from the immense gravitational potential of the Virgo cluster, the heart of our local supercluster. Other major attractors, like the Great Attractor and the even more massive Shapley supercluster, also exert their influence. When we calculate the expected velocity from the sum of all these gravitational potentials, we get a predicted motion that is very close to what we observe, but it's not a perfect match. There's a residual, a few tens of kilometers per second, that seems to be unaccounted for. This discrepancy suggests that our map of the mass distribution in the local universe might still be incomplete. There could be unseen structures, vast concentrations of dark matter that are pulling on us in ways we haven't yet fully charted. This leads to the fascinating concept of large-scale bulk flows. The idea is that not only is our local group of galaxies moving, but an enormous volume of space, perhaps hundreds of millions of light years across, is all streaming in the same general direction under the influence of gravitational forces that extend far beyond the largest structures we've currently identified. Our motion would just be a small part of this much grander cosmic river. Evidence for such bulk flows has been suggested by studies that measure the peculiar velocities of thousands of galaxies, their motion over and above the general expansion of the universe. Some of these studies have indicated coherent flows on scales that are surprisingly large, even challenging the expectation that on such immense scales, the expansion of the universe should dominate and everything should be essentially at rest with the Hubble flow. If these bulk flows are real and as vast as some data hints, it would imply the existence of gravitational sources of unimaginable size and power lurking just beyond the edge of our current observational horizon. The direction of the CMB dipole itself also holds a curious and perhaps coincidental puzzle. The hot spot, the apex of our motion, lies remarkably close to the alignment of the so-called axis of evil we discussed earlier. It also lies suspiciously close to the plane of our solar system. The probability of such an alignment happening purely by chance is low, and it immediately raises the question of whether there could be some unaccounted for local contamination affecting the measurement. Could there be a subtle foreground effect from within our own solar system or galaxy that is contributing a small fraction of the dipole signal? While the mainstream view holds that the dipole is overwhelmingly cosmological, a true Doppler shift from our motion, the persistence of these alignments ensures that a minority of scientists continue to investigate whether we might be seeing a tiny, blended signal, a whisper of new physics hiding within the roar of our own velocity. Ultimately, the CMB dipole is a story of perspective. It is the most personal of the CMB's mysteries, a direct result of our own journey through the cosmos. It serves as a constant reminder that when we gaze out at the universe, we are not passive, stationary observers. We are travelers moving at an incredible speed through a structured and dynamic universe, and the oldest light there is bears the imprint of our passage. The small discrepancies in its measurement are not flaws, but guides, pointing us toward a more complete understanding of the cosmic web that surrounds us and the hidden masses whose gravity shapes our path through the void. This curious lack of correlation on the largest scales is one of the most persistent and fundamental puzzles in our entire map of the primordial universe. It's not a single glaring anomaly like the cold spot, but rather a general quietness, a statistical hush that seems to blanket the cosmos on its very grandest dimensions. According to our most robust models of cosmic inflation, the quantum fluctuations that seeded all structure should be imprinted across the sky as a random field, meaning that even the largest patches of the CMB should show some degree of variation and correlation with their neighbors. And yet, when we analyze the data, the observed amount of correlation between these vast regions is significantly less than what our theories predict. It's as if the universe's largest bell was struck at the beginning of time, but the deepest, most resonant notes in its chord are mysteriously absent from the symphony we hear today. Scientists describe this using the power spectrum, a graph that charts the strength of temperature variations against their angular size. On the left side of this graph, representing the largest scales stretching across billions of light years, the line dips down. The power is missing. This isn't just a minor statistical wobble, it strikes directly at the predictions of the simplest inflationary models, which anticipate a certain level of structure on all scales. This missing power forces us to confront a few distinct possibilities, each with profound implications. The first and most conservative explanation is a combination of cosmic variance and foreground contamination. Cosmic variance is a unique and unavoidable challenge in cosmology. We only have one universe to observe. When we look at the largest scales, we are by definition looking at only a handful of these massive patches. There's simply no way to get a large statistical sample of something that is, by its nature, the size of our entire observable cosmos. It's like trying to determine the average height of humans by only ever measuring 3 people. Your result could easily be skewed by random chance. So, it's entirely possible that we just live in a part of the universe that happens to be unusually smooth on these immense scales. A statistical fluke that makes our local neighborhood appear special. On top of that, the delicate task of subtracting foreground contamination, the glow of our own Milky Way galaxy, and the dust within our solar system is incredibly difficult on these large angular scales. A tiny, systematic error in this cleaning process could easily artificially suppress the apparent power, creating a phantom lack of correlation where none truly exists. If the effect is real and not an artifact of our observation, the explanations venture into far more exciting territory. One compelling idea is that this is the signature of a finite universe. In an infinite, flat cosmos, there should be no upper limit to the size of fluctuations. But if the universe is finite and multiply connected, perhaps shaped like a 3-dimensional torus, then there is a fundamental limit. You simply cannot have a wave, a fluctuation that is larger than the universe itself. The lack of power on the largest scales would then be a direct reflection of this cosmic finitude, a natural cutoff because those ultra-large scales do not physically exist. The universe would be like a room that is too small to echo with the deepest notes. Alternatively, this missing correlation could be a fossil from the era of inflation itself. Perhaps the inflationary field had a specific property that suppressed the generation of the very longest wavelength fluctuations. Some models suggest a brief, fast roll phase at the very end of inflation, or a feature in the inflationary potential that would have effectively put a cap on the power of the largest modes. It's as if the process that generated the quantum noise had a built-in filter, preventing the largest ripples from forming. Another radical proposal involves the pre-inflationary universe. If the Big Bang was not the absolute beginning, but was preceded by a contracting phase or some other form of quantum gravity era, the conditions from that previous epoch could have imposed their own boundary conditions, effectively erasing the largest fluctuations before inflation could even amplify them. Each of these possibilities points toward a more complex and nuanced origin story for our cosmos, one that extends beyond the simple picture of a single, smooth inflationary field. This mystery of the large-scale missing power is therefore a deep probe into the geometry and the very first instance of the universe. It challenges us to distinguish between a simple statistical quirk of our own vantage point and a monumental discovery about the fundamental nature of reality. Whether it ultimately reveals a cosmos that is finite, an inflationary history that is more complex, or even a window into a time before the Big Bang, this quietness on the grandest of scales speaks volumes about the limits of our current understanding and the thrilling potential for a new cosmic paradigm. But beyond the temperature map, the primordial light holds another, even more subtle layer of information, a hidden text written in the very direction of its vibration. This is the polarization of the cosmic microwave background, and deciphering its two distinct languages known as E-modes and B-modes could unlock secrets ranging from the birth of the first galaxies to the violent tremors of the universe's creation itself. To understand polarization, imagine the surface of a calm pond. Now toss a single pebble into its center. The ripples that spread out are waves, and as they travel, they oscillate up and down in a specific direction. That direction is their polarization. The CMB light is made of photons, which are waves of electromagnetic energy, and they too have a preferred orientation of vibration stemming from their last interaction with matter billions of years ago. That final, fateful interaction was a scattering event. Just before the universe became transparent, a CMB photon likely scattered off a free electron for the very last time. The direction that electron was moving and the angle of that scattering imprinted a specific polarization direction onto the photon. By mapping the patterns of these polarized directions across the entire sky, we gain a powerful new lens on the physics of the early universe. The polarization patterns are separated into two distinct types, much like how we can describe any pattern of arrows on a sphere using a combination of two fundamental shapes, one with a curling, vortex-like quality and one without. The first type is called E-mode polarization, named for its similarity to the pattern of electric field lines around a charged particle. This is the dominant signal we see, and it is a direct descendant of the same density fluctuations that created the hot and cold spots in the temperature map. Think of those primordial sound waves compressing and rarefying the plasma. When a photon scattered off an electron in the hot, compressed crest of one of these waves, it received a different polarization imprint than if it had scattered in a cooler, emptier trough. The resulting E-mode pattern is a beautiful, curling field that points directly toward or away from the centers of the original density peaks. It doesn't tell us a new story, but it provides an independent and powerful confirmation of the density story we read from the temperature variations. It also gives us a clearer view of the later epoch of reionization, as the first stars and galaxies created free electrons all over again, causing a second round of scattering that added its own distinct large-scale E-mode pattern to the sky. The real prize, however, is the second type, b-mode polarization. This pattern is named for its resemblance to the magnetic field lines around a bar magnet, and its detection is the holy grail of modern cosmology. While E-modes are generated by the relatively straightforward scalar effects of density variations, B-modes can only be created by a very specific type of force, one that has a twisting, shearing quality. There are two potential sources for such a signal, and distinguishing between them is the key to unlocking the universe's deepest secrets. The first and more mundane source is gravitational lensing. As the CMB light travels for 13.8 billion years to reach us, its path is subtly bent and warped by the gravitational pull of all the matter, both dark and visible, that it passes. This weak gravitational lensing effect can gently twist the pristine E-mode patterns, converting a small fraction of them into a specific, predictable pattern of B-modes. This lensing B-mode signal has already been detected, and it is incredibly valuable. It provides a unique map of the distribution of all matter across the cosmos, offering a powerful, independent way in on the amount and clumpiness of dark matter. But the B-mode signal that captivates cosmologists is the primordial one, the signature that could only have been created by primordial gravitational waves. These are not waves in space-time, they are ripples of space-time itself, theorized to have been generated during the incredibly violent period of cosmic inflation. As inflation stretched the quantum fabric of the universe, it is believed to have amplified quantum fluctuations in the gravitational field, creating a background of these primordial waves. Their passage through the early universe would have literally stretched and squeezed space-time in a quadrupole pattern, imparting a unique, swirling handedness to the polarization of the CMB photons. This would create a distinct, large-scale pattern of primordial B-modes that is completely separate from the lensing-generated signal. Finding this specific fingerprint would be the most direct possible evidence that inflation occurred, and it would tell us the energy scale at which it happened. The amplitude of the B-mode signal is directly tied to the intensity of the inflationary energy. A strong detection would mean inflation was driven by energies 1 trillion times higher than those at the Large Hadron Collider, opening a window into grand unified theories and potentially quantum gravity. The hunt for these primordial B-modes is arguably the most technically demanding challenge in all of observational cosmology. The signal is incredibly faint, predicted to be more than 1 million times weaker than the temperature fluctuations. It is buried under a mountain of foreground contamination, the polarized light from dust grains in our own galaxy spinning in magnetic fields which can perfectly mimic the swirling B-mode pattern. This was the tragic flaw in the initial Bicep 2 announcement, a stark lesson in the perils of galactic interference. The quest now requires multi-frequency observations from the most sensitive telescopes on Earth, located at the driest, coldest places on the planet like the South Pole and the Chilean high desert, to meticulously separate the cosmic signal from the galactic noise. Any anomaly or unexpected feature in the B-mode spectrum, a different amplitude, a different scale dependence, or even its complete absence, would send shockwaves through theoretical physics. A signal stronger than predicted could point to more complex models of inflation or exotic fields. Its absence would force us to rule out a wide swath of the most popular inflationary models and send us back to the drawing board to conceive of entirely new ideas for how our universe began. The quiet whispers of polarization hold the potential for the loudest revolution in our understanding of cosmic origins. What if the strange features we see in the ancient afterglow of the Big Bang aren't glitches in our data or simple statistical flukes, but something far more profound, scars from a collision with another universe entirely? This idea pushes past the boundaries of our cosmic horizon and into the staggering possibility of the multiverse, suggesting that the largest anomalies in the cosmic microwave background could be our first empirical evidence that our universe is not alone. The cold spot, that colossal region of unexpected cold, and the hemispherical power asymmetry, which gives one half of the sky a different character than the other, become more than just puzzles. They transform into potential windows into a reality vastly larger and more bizarre than we ever imagined. The theoretical framework for this stems from certain models of eternal inflation. In this picture, our entire observable universe is just one bubble in a vast, endlessly frothing cosmic foam. The Big Bang wasn't a singular, unique event, but the moment our local bubble of space-time began its rapid expansion within a much larger, inflating meta-universe. In this infinite foam, other bubble universes are constantly popping into existence, each with their own potentially different laws of physics, constants, and dimensions. Crucially, these bubbles aren't necessarily static. They can move, grow, and if they are close enough, collide. When two such bubble universes meet, the energy released at their boundary would be unimaginable. It would be a cosmological event of the highest order, and the resulting shockwave would propagate through the interior of both bubbles, leaving a permanent, indelible mark on their structure. This is where the cold spot enters the picture as a prime candidate. A collision with another universe wouldn't create a random, messy splatter. The physics of such an event predicts a very specific signature, a somewhat circular imprint on the CMB sky where the temperature and polarization patterns are distinctly altered. The immense energy of the collision would have slightly diluted the plasma in that region, making it a vast, shallow gravitational well. As CMB photons traveled through this well, they would lose energy climbing out, experiencing a redshift that would make that entire patch of sky appear colder. The size, shape, and temperature profile of the cold spot align suspiciously well with what such a cosmic bruise might look like, a circular, low-temperature region that is difficult to explain through any known standard process within our own universe alone. Similarly, the hemispherical power asymmetry, where one half of the cosmos seems fundamentally different from the other, could be explained by a more glancing blow. If our universe grazed the edge of another bubble, the interaction wouldn't be a direct head-on collision creating a single spot, but a more sweeping directional event. The gravitational influence or energy injection from this encounter could have been uneven, affecting one entire hemisphere of our infant cosmos and creating a permanent, large-scale lopsidedness in the distribution of primordial fluctuations. This would account for why one half of the sky shows more pronounced temperature variations than the other, violating the expectation that the universe should be statistically uniform in all directions. The implications of such a discovery would be nothing short of earth-shattering for physics and philosophy. Confirming a multiverse through a CMB imprint would radically extend the scale of physical reality, suggesting that what we call the universe is just a tiny province in an infinite cosmic archipelago. It would provide a potential explanation for the seemingly fine-tuned constants of nature that allow for our existence. In an infinite multiverse, every possible set of physical laws will be realized somewhere, and we naturally find ourselves in one of the bubbles where conditions are right for life. We would have to fundamentally reconsider our place in the cosmos, not just as inhabitants of a planet or a galaxy, but as residents of a single bubble in a froth of countless others. Of course, the scientific community approaches this idea with extreme caution, and for good reason. The multiverse is, by its very nature, a profoundly difficult hypothesis to test. Critics argue that invoking other universes to explain anomalies can become a catch-all, a way to explain away any discrepancy without offering concrete, falsifiable predictions. The primary challenge is to find a signature in the CMB that cannot be plausibly created by any other known physical process within our own universe. This requires building even more precise models of what a bubble collision would actually look like, predicting not just its temperature signature, but also its unique polarization patterns and its specific effect on the statistical properties of the fluctuations. The hunt is on for a smoking gun, a pattern so specific and so unlikely to occur by random chance or through standard physics that the multiverse becomes the only viable explanation. Until that evidence is found, these cosmic anomalies remain tantalizing hints, the most thrilling kind of mystery, one that promises to rewrite not just our textbooks, but the very definition of reality itself. Determining the age of the universe might seem like an impossible task, but the cosmic microwave background provides us with the most precise cosmic clock we have, yielding an age of 13.8 billion years with astonishing accuracy. This isn't a single, simple measurement. It's the result of a complex and beautiful piece of cosmic detective work that uses the CMB's detailed pattern as the ultimate input for a model of cosmic evolution. The process begins with the fact that the CMB is a snapshot of the universe at a very specific moment in time, when it was 380,000 years old. The precise patterns of hot and cold spots in that snapshot encode a wealth of information about the contents of the cosmos at that epoch, the amounts of ordinary matter, dark matter, and dark energy, as well as the current rate of expansion. Scientists use these measured ingredients as the initial conditions in the equations that describe how the universe expands and evolves. By running the model backwards to the Big Bang and then forwards to the present day, they can calculate the total elapsed time, arriving at that definitive figure of 13.8 billion years. This value isn't just pulled from thin air. It's the only age that allows all the pieces of the puzzle, the fluctuation sizes, the peak ratios, the observed expansion rate, to fit together into a single, coherent picture. The true power of this method lies in its cross-checking with completely independent techniques, creating a robust web of evidence that bolsters our confidence. The other primary method for dating the universe involves measuring the expansion rate, the Hubble constant, locally using stars and supernova, and then extrapolating backwards. While the local measurements currently give a slightly different value for the Hubble constant, causing the tension we discussed earlier, the age they infer is still remarkably close, also hovering right around 13.8 billion years. We can even check this age by dating the oldest objects within the universe itself. The most ancient stars in our galaxy, found in globular clusters, have been aged using stellar evolution models. The oldest of these stars are consistently measured to be around 13.4 billion years old. The fact that stars are younger than the universe itself is a crucial and satisfying sanity check. It would be a profound problem if we found objects that appeared to be older than the cosmos that contains them. This multi-pronged agreement is a monumental triumph for modern cosmology, suggesting that our standard model is overwhelmingly correct in its broad strokes. However, the presence of anomalies within the CMB data itself invites a fascinating question. Could these subtle wrinkles point to a need for a revised timeline? If our model of the universe's contents or its expansion history is even slightly incorrect, it would change the calculated age. For instance, if dark energy is not a constant force but has been evolving over time, growing stronger more recently than we assume, it would alter how we calculate the past expansion rate. A dynamic dark energy that was weaker in the past would mean the universe expanded more slowly for longer than our models suggest. To still arrive at the current observed size and temperature of the universe, this would force the initial starting point, the Big Bang, to have occurred further in the past. In this scenario, the universe could be older than 13.8 billion years. Conversely, a different history for dark matter or the presence of additional relativistic particles in the early universe could tweak the expansion history in the other direction, potentially suggesting a slightly younger cosmos. The pristine data from the CMB is the anchor that allows us to test these exotic possibilities. The incredible precision of the Planck satellite measurements has tightly constrained how much these other parameters can vary, fiercely protecting the 13.8 billion year age. Yet, the very existence of the Hubble tension suggests that our understanding of the expansion history might be incomplete. This discrepancy means that if the local measurement of the expansion rate is correct, then our interpretation of the CMB data must be missing something that reconciles the faster current expansion with the early universe conditions. Any such modification to the model, whether it's early dark energy, interacting dark sectors, or even a slight curvature, would have a knock-on effect on the inferred age. Currently, none of these proposals have significantly shifted the central value, but they remind us that the 13.8 billion year figure is the product of a specific model. The CMB doesn't directly tell us the age. It provides the data that, when fed into our best model of physics, gives us that result. If the model needs refinement, the age could be refined with it. This isn't a weakness but a strength of the scientific process, demonstrating how our knowledge evolves with ever more precise observations and deeper theoretical insight. The age of the universe remains one of our greatest scientific achievements, a number etched into the ancient light, yet it remains open to interpretation as we continue to decode the full story hidden within the cosmic background. Yet for all its profound implications, this ancient light does not reach our telescopes in a pure, unadulterated form. It arrives as a faint signal buried beneath a cacophony of modern cosmic noise, and the monumental effort to clean this data might be inadvertently creating some of the very mysteries we seek to solve. This is the critical challenge of foreground contamination, a pervasive and deceptive interference that forces us to ask a humbling question. Are some of the anomalies we've been exploring not features of the primordial universe, but merely phantoms in our data processing? Imagine trying to listen to a faint, distant symphony while standing in the middle of a roaring factory. The music is there, but it's completely overwhelmed by the industrial din. This is the essential problem faced by cosmologists. The pristine whisper of the cosmic microwave background must pass through our own vibrant, messy galaxy to reach us. The Milky Way is filled with all manner of emitting material that shines brightly at the same microwave frequencies we use to study the CMB. There are two primary culprits. The first is galactic dust, microscopic grains of silicon and carbon, smaller than a wavelength of light, that are spun up by interstellar magnetic fields and emit polarized radiation. The second is synchrotron radiation, a brilliant glow produced by high-energy electrons spiraling at nearly the speed of light along the galaxy magnetic field lines. Both of these foregrounds emit light that can perfectly mimic the patterns we are desperately searching for in the CMB, especially its subtle polarization signals. The process of separating this galactic noise from the cosmic signal is known as component separation, and it is one of the most complex and fraught steps in modern cosmology. It's not a matter of simply hitting a delete button for the Milky Way. We don't have a perfect, pre-existing map of this foreground contamination. Instead, satellites like Planck observe the sky at multiple different frequencies, from radio waves to high-frequency microwaves. The key is that the foregrounds and the CMB have distinct spectral signatures. Their brightness changes in unique ways across these different frequencies. The CMB has a perfect blackbody spectrum. It looks exactly the same no matter what frequency you observe it at, aside from the Doppler shift of our motion. Galactic dust, however, gets much brighter at higher frequencies, while synchrotron radiation fades away and becomes brighter at lower frequencies. By observing at 9 different frequencies, the Planck team could create a kind of chemical fingerprint for the light in each pixel of the sky, using sophisticated statistical algorithms to estimate and subtract away the contribution from dust and synchrotron radiation, hopefully leaving behind only the pristine CMB. The problem is that this process is extraordinarily delicate and filled with potential pitfalls. Our models for how galactic dust and synchrotron radiation behave are based on incomplete information. Dust grains of different sizes and compositions might have slightly different emission properties in different parts of the galaxy. The magnetic fields that align the dust and power the synchrotron radiation are not perfectly mapped. If our template for the foregrounds is even slightly inaccurate, the cleaning process can either leave behind residual contamination or, even worse, subtract out something that was never there to begin with, creating a false feature. It's like using an imperfect sieve to separate sand from gold dust. You might accidentally throw away some gold, or you might be left with bits of sand that you mistakenly believe are precious metal. This is where the connection to our cosmic anomalies becomes so critical. Many of the large-scale anomalies, like the elusive axis of evil alignment or the hemispherical power asymmetry, are most prominent on the very largest angular scales. Ironically, these are the scales most vulnerable to foreground contamination. Why? Because the Milky Way galaxy itself is a large-scale structure that spans the sky. Imperfectly modeling and subtracting its diffuse, all-pervasive glow can easily introduce large-scale artifacts into the clean CMB map. A slight miscalibration in how we handle the dust in the galactic plane could create a false dipole or quadrupole moment. A residual pattern from synchrotron emission could mimic a specific polarization signal. The cold spot itself sits in a region of the sky that is relatively free of foregrounds, which is why it's so compelling, but other, subtler anomalies might not be so immune. The scientific teams behind WMAP and Planck are acutely aware of these challenges and have developed multiple independent methods for foreground subtraction to cross-check their results. They run different algorithms, Commander, NILC, 7 each with their own philosophical approach to separating the signals. The fact that many anomalies persist across these different cleaning techniques is what gives them credibility and keeps scientists searching for cosmological explanations. However, the possibility of a systematic error common to all methods can never be entirely ruled out. The recent, more precise data from Planck has actually weakened some of the anomalies, suggesting that better foreground modeling might be gradually erasing them, a hint that they may indeed be phantoms of our data processing. This constant, careful negotiation between signal and noise is the unglamorous backbone of cosmology. It requires a profound humility, a recognition that our view of the ultimate past is filtered through the messy reality of our present galactic address. Every claim about the primordial universe must be weighed against the possibility that we are still seeing the ghostly echo of our own Milky Way, a reminder that the most difficult obstacles to understanding the cosmos often aren't in the distant heavens, but in the intricate challenge of correctly interpreting the faint and precious light that finally reaches us. Yet as we peel back the layers of the cosmic microwave background, moving from the grandest scales down to the finest details, we encounter a subtle but crucial silencing of the universe's primordial symphony. This is the phenomenon known as the silk damping tail, a gradual fading of the temperature fluctuations on the very smallest scales, and it provides a powerful and independent test of the conditions in the infant cosmos. The name itself comes from the astrophysicist Joseph Silk, who first predicted this effect in the 1960s, and it represents the final chapter in the story of the primordial sound waves, the point where the music of creation doesn't just stop, it quietly fades away. To understand why this happens, we need to revisit the final tumultuous days before the universe became transparent. Up until the moment of recombination, the cosmos was a tightly coupled plasma, a thick soup where photons, electrons, and atomic nuclei were constantly colliding. This constant interaction is what allowed the pressure waves, the baryon acoustic oscillations, to propagate through the medium like sound through air. But as the temperature dropped, this tight coupling began to loosen. The density of free electrons plummeted as they were captured to form atoms, meaning photons had to travel further and further between collisions. This increasing freedom had a critical consequence for the smallest ripples in the plasma. The very shortest wavelength sound waves, the highest pitched notes in the cosmic chord, began to dissipate their energy. Photons could now diffuse out of the compressed regions of these tiny waves, carrying their energy with them and effectively smoothing out the wrinkles before they could be frozen into place. It's akin to the high-frequency details in a musical recording being the first to be lost to background static. The deepest bass notes ring clear, but the sharpest treble fades into a gentle hiss. This process imprints a specific, predictable signature on the power spectrum of the CMB. If you look at a graph plotting the strength of the fluctuations against their angular size, you see a series of sharp harmonic peaks representing the resonant sound waves. But as you move to the right to higher multipole moments representing smaller and smaller scales, those peaks don't just continue, they rapidly diminish in amplitude, tailing off into statistical noise. This steep drop-off is the damping tail. Its precise shape is not arbitrary. It is exquisitely sensitive to the fundamental parameters of the universe at that time. The rate at which the fluctuations dampen depends directly on the density of baryons, the ordinary matter, present. A higher baryon density would have allowed the plasma to hold onto the sound waves for a bit longer, altering the steepness of the damping slope. It also depends on the rate of expansion of the universe at that epoch, which is governed by the amount of dark matter and dark energy. By measuring the exact point at which the primordial fluctuations are washed out, we gain a powerful, independent check on the cosmic ingredients we've measured from the positions and heights of the acoustic peaks. The incredible precision of the Planck satellite's measurement of this damping tail has turned it into a stringent test for our entire cosmological model. The observed tail matches the predicted shape from the lambda cold dark matter model with remarkable accuracy, providing a resounding vote of confidence for our standard recipe of the universe. But its importance extends far beyond mere confirmation. This detailed map of the damping tail offers a unique window into the very beginning of inflation itself. The primordial power spectrum, the initial distribution of quantum fluctuations that inflation stretched across the cosmos, is predicted to be nearly, but not perfectly, scale invariant. This means the strength of the fluctuation should be almost the same on all scales, but it might have a tiny tilt, a slight preference for larger or smaller waves. The damping tail, by revealing the behavior of the smallest possible scales, allows us to probe this tilt with incredible precision. Any significant deviation from the expected damping could signal features in the inflationary potential, hints of a multi-field inflation scenario, or even the presence of primordial magnetic fields or other exotic physics that would have altered the diffusion of photons. In the silent whisper of the damping tail, we find not an end but a delicate and precise probe, allowing us to listen for the faintest echoes of the universe's very first moments, testing the limits of our understanding on the smallest scales imaginable. But perhaps the most chilling prediction informed by the CMB's composition is the concept of heat death. This is not a dramatic, explosive end, but a quiet, gradual fading into eternal stillness. The CMB shows us a universe that began in a state of incredibly high temperature and density, and it has been expanding and cooling ever since. This expansion is not just spreading matter out, it's diluting the useful energy available to do work, a quantity known as entropy. The CMB itself is the ultimate evidence of this process. A once searing blast of radiation cooled to a mere 3 degrees above absolute zero. If dark energy continues to accelerate this expansion indefinitely, as the CMB data currently suggests it will, then the universe is on a one-way trip toward maximum entropy. Billions of years from now, long after the last stars have burned out and the last black holes have evaporated via Hawking radiation, the universe will become a vast, dark, and incredibly cold emptiness. The temperature will approach absolute zero, and no energy gradients will remain to power any processes or any form of life. It will be a static, eternal, and lifeless equilibrium, the ultimate silence following the cosmic symphony whose first note we see in the CMB. This seemingly inevitable conclusion, however, is precisely where the CMB's anomalies invite us to question our assumptions. Our entire prediction of heat death rests on the idea that dark energy is a cosmological constant, unchanging and eternal. But what if it isn't? The Hubble tension, that stubborn disagreement over the current expansion rate, could be the first hint that our understanding of dark energy is flawed. Perhaps dark energy is dynamic, a force that evolves over time. Some theoretical models propose a form of dark energy called phantom energy, which would have a terrifying consequence. Instead of just accelerating expansion at a constant rate, the strength of phantom energy would increase over time. This would lead to a far more violent end than heat death, the Big Rip. In this scenario, the accelerating expansion wouldn't just push galaxies apart. Eventually, the repulsive force would become so strong that it would overcome the gravity holding galaxies together. Then it would rip apart stars from their galaxies, planets from their stars, and finally tear apart atoms and even the very fabric of spacetime itself. The universe would end not with a whimper, but with a catastrophic, fundamental shredding of reality. While the standard CMB analysis favors a cosmological constant, the persistent anomalies keep the door open for more exotic and terrifying possibilities. On the opposite end of the spectrum lies the once favored Big Crunch, a cyclical vision of cosmic death and rebirth. Before the discovery of dark energy's acceleration, many cosmologists believed the universe might have enough matter to eventually halt and reverse its expansion. Gravity would pull everything back together in a mirror image of the Big Bang, culminating in a fiery collapse into a singularity. The CMB played a pivotal role in largely ruling out this fate. The precise measurements of the universe's geometry from the CMB's fluctuations show a universe that is flat, which means its density is at the critical value. However, the vast majority of this density is in the form of dark energy, which exerts a repulsive, not attractive force. The CMB data tells us there is simply not enough attractive matter, whether normal or dark, to overcome the relentless push of dark energy and cause a recollapse. The Big Crunch, for now, appears to be off the table. Yet, the CMB's own anomalies, particularly those suggesting a possible slight positive curvature, leave a tiny window open for a cyclical universe. If future, more precise measurements were to confirm that the universe is indeed closed, however slightly, it would resurrect the possibility of an eventual collapse, though it would require dark energy to somehow decay away in the distant future. Furthermore, some speculative theories suggest that the constants of nature, like the strength of dark energy, might not be truly constant but could change over cosmological timescales. A few of the large-scale anomalies in the CMB, like the hemispherical power asymmetry, could be incredibly faint hints of such an instability, a suggestion that the rules of the game might not be fixed from one end of the cosmos to the other, or from one eon to the next. If the fundamental forces are in flux, then predicting the ultimate fate becomes nearly impossible. Ultimately, the cosmic microwave background is our most powerful crystal ball. It provides the initial conditions, the starting recipe from which we extrapolate the entire future history of the cosmos. Its current data paints a picture of a cold, lonely, and eternal fate in the form of heat death. But the small, unresolved cracks in that data, the tensions, the asymmetries, the unexpected alignments, are the most valuable part of the story. They are the cosmic whispers suggesting that our model, for all its spectacular success, might still be missing a crucial piece of the puzzle. They remind us that the fate of the universe is not yet written in stone, but is an epic story still being decoded, with its final chapters waiting to be revealed in the subtle, ancient light that fills the sky. Yet after all we have explored, from the faintest whispers of polarization to the grandest questions of cosmic fate, the most humbling truth is how many profound mysteries of the cosmic microwave background remain stubbornly unresolved. The cold spot continues to defy a comfortable explanation, its chilling presence a constant reminder of potential physics beyond our grasp. the so-called axis of evil, with its unnerving alignment to our own solar system, persists as a statistical ghost that refuses to be exorcised by better data. The Hubble tension stands as the most significant crack in our cosmological model, a 5 sigma discrepancy between the early and modern universe that threatens to unravel our understanding of cosmic evolution. And the haunting lack of large-scale correlation, the unsettling quiet on the grandest of scales, whispers of a universe that might be finite, or of an inflationary beginning more complex than we ever imagined. These are not minor puzzles, they are fundamental challenges that suggest our standard model, for all its glorious success, is an incomplete picture of reality. This is not an end but a new beginning, a catalyst for a bold new generation of observatories designed to listen more closely to the ancient light than ever before. The upcoming LIGHTBIRD mission, led by the Japanese Space Agency, is a dedicated satellite designed with one primary goal: to hunt for the elusive primordial b-mode polarization with a sensitivity that finally surpasses the confusing fog of galactic dust. By observing the entire sky from the stability of space, it aims to provide a definitive, all-sky map of this signal, either confirming the simplest models of inflation or sending theorists back to the drawing board. On the ground, the colossal CMB-S4 project represents a staggering leap in scale. Imagine not 1 or 2 telescopes, but a coordinated network of 21 instruments deployed at the South Pole and in the high Chilean desert, working in unison with an unprecedented 500,000 detectors. This vast array will measure the CMB's temperature and polarization with such exquisite precision that it could detect the gravitational wave background even if its signal is a fraction of what some models predict, while also providing the ultimate clarity on the anomalous large-scale patterns that have perplexed us for decades. But the quest to understand the cosmos doesn't end with the CMB itself. The James-Webb Space Telescope, though not a CMB instrument, plays a crucial supporting role in this cosmic detective story. By peering back to the very first galaxies and stars, it provides an independent and critical timeline for the epoch of reionization. Its detailed observations of the earliest cosmic structures will help us understand the initial conditions that the CMB's fluctuations seeded, offering a vital cross-check on the story told by the ancient light. The synergy between these missions is what makes this era so thrilling. JWST looks at the result of the cosmic blueprint, while CMB-S4 and LIGHTBIRD examine the blueprint itself. Together, they form a complete picture from the first quantum seeds to the glorious tapestry of galaxies we see today. What they might find is the true source of excitement. The goal is not merely to confirm what we already know, but to be surprised. These instruments are so sensitive that their greatest discovery could be something entirely unforeseen, a signature of cosmic strings, a definitive distortion in the CMB's spectrum revealing exotic particle decay, or a polarization pattern that points unequivocally to a multiversal collision. They could finally resolve the Hubble tension, revealing whether the solution lies in early dark energy, new relativistic particles, or a fundamental flaw in our understanding of gravity. Every lingering anomaly is a potential doorway, and these next-generation missions are the keys crafted to unlock them. We stand on the precipice of a new revolution in cosmology, where the faintest whispers from the edge of time are finally about to be heard, promising to rewrite our story of the universe from its very first moment to its ultimate, distant end. From the horizon problem's perfect smoothness to the startling chill of the cold spot, from the unsettling alignments of the axis of evil to the missing base notes of the universe's largest fluctuations, these 30 mysteries are far more than a simple checklist of cosmic quirks. Each one represents a profound question mark etched into the oldest light in existence, a direct challenge to our most cherished cosmological models. They are not failures of our understanding, but rather guideposts pointing the way toward a deeper and more complete theory of reality. What appears to be a map of a perfectly predictable cosmos is, upon closer inspection, filled with intriguing wrinkles and puzzling imperfections that collectively whisper of physics operating at scales and energies we can scarcely imagine. This journey through the cosmic microwave background has taken us from the universe's very first second, with its sea of primordial neutrinos, to the possibility of its final, cold demise in heat death. We've grappled with the Hubble tension, a modern crisis that threatens to rewrite our cosmic timeline, and explored radical ideas like early dark energy and interacting dark sectors that could provide a solution. We've considered the ghostly influence of cosmic strings, the staggering possibility of a multiverse leaving its bruise on our sky, and the relentless, meticulous hunt for the faint swirls of primordial gravitational waves in the CMB's polarization. Each mystery interlocks with the others, suggesting that the solutions may not be isolated fixes but parts of a grander, unified picture we are only beginning to glimpse. The true value of these enigmas lies in their power to propel science forward. They are the unresolved chords in the symphony of the Big Bang, creating a compelling tension that drives the next generation of explorers to build ever more sensitive instruments. Missions like LightBird and CMB-S4 are not merely incremental upgrades. They are direct responses to these puzzles, designed to listen to the ancient light with a clarity we have never before possessed. They are our best hope for turning these tantalizing hints into definitive discoveries, for transforming statistical anomalies into new chapters of physical law. So as we look up at the silent, microwave glow that permeates all of space, let's remember that we are not looking at a static relic of a dead past. We are witnessing a dynamic, living puzzle, a cosmic story that is still being written and decoded. The greatest breakthroughs in our understanding of the universe, from the nature of dark matter and dark energy to the possibility of other realities, are likely hidden within these subtle patterns, waiting for the keen eye and the brilliant mind to uncover them. Stay curious, for the next great discovery is written in the light all around us, and it is waiting